Right, good afternoon, grade 11s, and welcome to the session on acids and bases. And we will also look at redox reactions a little bit later in the afternoon. I'm Mrs. Goodyear, and I am all the way from Grahamstown in the Eastern Cape. And today we are going to look at one of my favorite sections. And I say that about many of the sections that we do cover in chemistry, but this ultimately is one of the most fun sections, just because you're starting to use some of your basic knowledge and theory that you've learned already and that you've acquired on the sections on intermolecular forces. A little bit, obviously, of acids and bases come down to equilibrium. And so every time when I start that, I can just imagine that some of you get quite a bit of a shock because schools do it in a different order, all of these sections. Like the school that I'm teaching at, we don't do a little bit of each in every grade. We do acids and bases from start to finish in grade 11, and then we don't revisit it again until the prelim or until the trial exam. So what I'm going to do this afternoon, hopefully, is just to settle you down a little bit, because this ultimately is one of the sections that is not well answered at the end of a grade 12 year in the IAB exam, and I think in the GDE exam as well. So as we've got both parties present, please just be patient. There might be a little bit of the slides or the notes that is not really applicable to you because you might be DBE or IAB. But yeah, let's get going and make the most of this afternoon. Please, can I remind you at any point, if you've got any questions, you can just type them out in the chat. I do look at the chat very often. And if I do not answer your question immediately, it might just be because it is incorporated in an answer coming close to when you've answered or asked it. All right, so let's get going. So the first thing that I want to point out, and it's usually quite a little bit of a boring bit, I would say, is the history in chemistry. No one ever wants to sit and study that, so I'll just keep it short. But with regards to acids and bases, there are many theories, I want to say, and many scientists that have different outlooks as to what is an acid and what a base is and why they react the way in which they do. But Arrhenius, this was the first little way in which people back in the day used to see acids and bases. And that was the substance that produces hydrogen ions, or then we know them also as hydronium ions, when dissolved in water. So when it was dissolved in water, it was produced. They were there, they were present. And if you think back to your prep school or your preschool, even, I know that some younger kids are now introduced to acids and bases, but you can immediately feel the difference of an acid and a base, even on your fingertips, in your mouth. You can definitely taste the difference. I always ask my junior grades what face do you pull if you eat a sour worm? And you see them pull their faces, and then we look at where you taste the acid and where you would taste a base and salt and sweet, etc. So for this afternoon, let's make chemistry relevant. Let's make it something that we actually can relate to every day. I mean, we all eat, we all enjoy food, and that is your first interaction actually with acids and bases, if we think about it. All right, so back to the basics. An acid produced hydronium or hydrogen ions. That is what we used to know it as. And a base is a substance that produces hydroxide ions. Now, going from Arrhenius to the Lowry-Bronsted theory, it's not really very different. And you can't say that they are complete opposites or polar opposites. It's very similar. But the one thing that is different between Arrhenius and Lowry-Bronsted is not just that hydronium ions are produced and hydroxide ions are produced, but there's a transfer of what we refer to as a proton. And that is a hydrogen ion. And so I explained it to my classes the other day. This is the section that we're actually currently busy with the grade 11s, is if you think about hydrogen and where it is placed on your periodic table, we know it to be all the way to the left at the top, and very often students confuse it with being a metal. But why would it be all the way to the left in position 1 is because we know that it has one proton, and elements are placed on the periodic table based on their number of protons, and therefore we know that the electrons will increase as you go from one element to another. So yet again, for today, we're not just going to dig into the most challenging bits and pieces of this section, but I need to remind you of fundamental basics as we go. All right, so something like why hydrogen is position 1. All right, so with that, there is an interaction or a transfer, a donation and a receiving of a hydrogen ion, which you can refer to then as a proton. And I know in our junior grades or in our younger grades, we were told, no, only electrons can be transferred. But if you are transferring a hydrogen ion, it only has one proton. So therefore, we can refer to it as the proton that is being transferred from one substance to another. So an acid will always be a proton donor. So the acid, whenever you write an equation today, you'll see that I often do the arrow and the H plus away from the acid. So for instance, hydrochloric, we'll always try to do the acid, the arrow away from the acid, and then usually your arrow towards your base. As we know now that your base not only forms hydroxide ions, but your base is referred to as a proton acceptor. So whether it is DBE or whether you are IEB, I want to really encourage you to always refer to the correct definition. So as we go through the work today, there are many definitions, then there are many explanations of a term. And when in a test, and I know we're not going to start thinking about tests now, we'll do that at the end when we do some questions, but whenever you are asked to explain your understanding, you don't have to define. You can actually use your own words and maybe a variety of vocab in order to do so. Right, but those two are definitions. Hydrogen is usually the proton that is either donated by an acid or accepted by a base. Right, when we look at the term acid proticity, it's usually just where and how the proton is transferred. So you get substances that can donate more than one proton. So if you think about the example, which we've used just in the previous slide, HCl. HCl, the ratio of hydrogen atoms to chlorine atoms or chloride ions then is 1 to 1. 1H, 1Cl. How would you know that? A little bit of revision of writing a formulae based on the subscript. And we know that the subscript, the little number, small number, is always relevant to the element that it is written after, so the element before it. So we do not write ones in chemistry. So I know that this is a grade 1 rookie error, or grade 8 rookie error rather, but you do not write the ones in chemistry. We know them just as place or space keepers. All right. So when you look at HCl, hydrochloric acid, an acid which many of you might be familiar with by now, but hydrochloric acid has one proton to donate. If it does donate its proton, don't worry about what substance it's donating it to. We will get there. Then if it loses the H plus, you're going to be left with Cl minus. So hydrochloric acid is a monoprotic acid. We use the term monoprotic. Mono meaning one. Hydrochloric acid has one proton that it can donate. I want to scroll across. Sorry, I always do little notes before we start to make sure that we don't waste time in me writing and trying to write neatly. If you look at this, which is sulfuric acid has 2 hydrogen atoms, and then sulfate, which is a polyatomic ion with a charge of 2 minus. And we know that hydrogen is 1 plus, and therefore there must be 2 hydrogen atoms when you write your formula. Now, with that in mind, that should tell us that sulfuric acid doesn't just have 1 proton to donate, it can donate 1 hydrogen or 1 hydrogen ion, a proton, to 1 water molecule. But then what will you be left with? So I'm going to do it in steps. You'll see that you've got phosphoric acid as the example. I don't just read through examples. I usually think of other examples too. So let's look at this one. If sulfuric acid donates its 1 proton, what will you be left with? You had H2, you're now going to have H, SO4, and remember that it was neutral, and now you've lost a positive charge. So you're going to, I say you, but HSO4 is going to become negative by 1. I do know that some students like writing the 1 in there. You know that the 1 is optional, but the charge on that is negative. So now what can happen is we know that the sulfuric acid has donated that 1 proton. So if you had H2O, what will you now be left with? You will have H3O. And remember that the charge, the proton, the charge goes with. So if I had H2O, it's going to become H3O. And if it was neutral and it gained a positive charge, you're now going to have H3O plus. And this is what we refer to as the hydronium ion. So I know that some of you have maybe completed this section at school, but this is an in-depth class. So I really want to revisit all of these little bits and pieces just to make sure that we cover all of our bases and it's a level and an equal playing field. All right, but now we're not done because there is still 1 proton that can be donated. So now in your second step, and you'll see a little trick eventually. Now you start with HSO4 minus, and it's going to donate its proton to a different water molecule. The trick here is that every acid can donate one proton at a time. And once I've donated to this water molecule, that is now an hydronium ion. So you're done with it. And now in the next step, your H that you've got left, your proton that you've got left, or the 2 or the 3 that you've got left, depending on the example and the acid, that proton will then be donated to another water molecule. So please note, you're never forming H4O plus 2 and none of that, none of that. So now if you donate, or if this substance donates its last proton to a second water molecule, and I'm going to show the donation of and where that proton goes, you'll see that you will now have SO4. You've lost the 1 proton in the first step, the second proton in the second step. And now if the charge already was negative by 1 and you are losing another proton, what's the charge that goes with a proton is positive. So if you're negative by 1, it's now going to become negative by 2, and you will have your second hydronium ion. Right, so this is one first example. I am going to look at phosphoric acid as well. However, I want to take it one step further for those who like being challenged. And so you'll see that this is step 1, first proton, step 2. If your acid that you start off with has 1 hydrogen atom in its little bond at first, then you know that there will be 1 step, hydrochloric acid. You run out of protons after 1 step. If it is H2SO4, you'll have 2 steps, 1 proton, second proton. 2 hydronium ions were formed. So what I have seen, even in grade 11 papers, and excuse my very skew line, is I have seen some teachers actually ask you to write the net equation. And the net, or the overall equation. And please remember that when you write, whenever you write an overall equation, it merely means that you go from your first reactant. You ignore all of the steps. If there are 3 steps, 4 steps, you ignore all of the steps, but you go from your first reactant or first reactants, and you link that to your final product. Wouldn't you agree that that gives you a holistic picture of your overall or your net equation? So your final equation will then be whatever you started off with, H2SO4 plus H2O. And now you're just writing your final product as well. And we know that we finished off with sulfate, which is also a polyatomic ion. This usually blows the minds of my students, whereas in grade 11, you realize where your polyatomic ions come from. It used to be an acid that donated its protons, and now that is what's left, and that's what we refer to as your polyatomic ion. Always remember that reactions have to be balanced, and the chemical equation always needs to be balanced because you have to account for every reactant on your product side. And here's the little trick. Never call it a cheat, a trick. How many water molecules did we use? 1, 2, so you plug a 2 in there. How many hydronium ions did we form? 1, 2, plug a 2 in there, and it should be balanced. You can count if you do not trust me, but it should be balanced. All right, so with that in mind, I am going to look at the example that you have. I do believe that there's also power in the notes because you can see and you can listen to the explanation. So they're just explaining that proticity, or to be monodi, triprotic, or amphiprotic is also a term that I've heard, is some acids are able to donate more than 1 proton. The number of protons that an acid can donate is referred to as the acid proticity. Right. If it is polyprotic, what does poly mean? Poly means numerous. So if it's monoprotic, 1, if it's diprotic, 2, if it's triprotic, 3, or if you just want to throw di and tri out, I know that the IAB students, you merely just need to know monoprotic and polyprotic. So if we talk about a polyprotic acid, it is an acid that can donate numerous, and you do not have to specify how many. You can say numerous or more than 1. But I mean, if you have the example, why not specify? All right, so for all students, this example, you'll see that they now do your steps. I'm going to number them. Step number 1, step number 2, step number 3. Step number one, you started with phosphoric acid. It donated 1 proton, and therefore it has lost 1. And you'll see what they did here is they merely just showed the loss of the proton. They didn't show the reaction with water. So this is merely just to explain what happens to the proton. You lose it, but you've got 2 left. You lose another, you've got 1 left. You lose the third one, you've got nothing left, and that is the final process. All right. But please note that all acids, and that's where we're going to get now, all acids react with water, and that reaction we're going to distinguish between the difference between when acids and bases either dissociate or ionize. Right, and that is where we are going. Right, you're doing well. I'll say that a lot of times during the course of the afternoon because it's quite a long one. All right, so another little bit of basics, which I think is very confusing if we rush through it, but actually the concept is very, very simple. Okay, so here we go. When we look at conjugate acid-base pairs, a lot of new words maybe and difficult phrasing, and this is what it is. An acid forms a conjugate base, and now even in that, you're like, what is a conjugate base? Conjugate pairs is one reactant from the left-hand side of your reaction and one product from the right-hand side of your reaction. They look incredibly similar, very similar, but they differ by one thing and one thing only, and that is a proton, an H+ ion. So I'll repeat, if you are a bit confused as to how to identify acid-base conjugate pairs, it really is not just a random selection. Oh, I think this one, oh, and maybe this one. You identify one substance, so identify the acid on your reactant side, because they are usually the easy ones. An acid is a hydrogen atom, or an ion if you think about the bonding that it forms, but hydrogen attached to a halogen. I'm doing this because group 7, or a hydrogen attached to a polyatomic ion. And so the acids are usually the easy ones to identify. So if you want to know which substances are conjugate acid-base pairs, then identify your acid on your reactant side. We're going to do an example now. You identify it, and then you look for the substance on your product side that looks very similar, but if I were to just look at them quickly, there's an H+ missing on the one side or an H+ extra on the other. So they differ by a proton, and only one of them. So let's look at an example. Here we see that you've got nitric acid, HNO3. So you'll see as we go, I'll remind you of the names. They're incredibly important. So we've now dealt with HCl, which is hydrochloric. And now the second, oh, we've actually dealt with sulfuric as well, H2SO4. And then the last one of your strong acids, which we'll get to eventually, is HNO3 nitric acid. All right. So nitric acid reacts with water. Firstly, let's recap. What do we know? Larry Bronsted says that an acid is a proton donor. Okay, so you'll see we're not just going to go through every slide or every little bit of notes. I keep on jumping back because revision as we go. All right, so nitric acid, that is the acid. It will donate its proton. So let's see. If we had HNO3, what will we now be left with? NO3 was neutral, lost a positive charge. If you lose positive, you become negative. If you lose negative, you become positive. So there we go, lost its positivity or its positive charge, and therefore you've got NO3. That should ring a bell. If you think about your polyatomic ion table, which by the way, you are not provided with in your exams as far as I'm aware. So NO3 is nitrate, right? So now with nitrate, you'll see that what happens? Where did your H+ go? It went to your water. So H2O will now become H3O+. Please remember to write your phases. Sorry, I'm not leading by example today. We're going to practice to write our phases all the way as we go. All right, so there we go. Now that we've done this, we have really not answered the question. Identify our conjugate acid-base pairs, right? There is HNO3. It is an acid. What substance on the product side, looks very similar but differs with an H+? I'm going to highlight them exactly the same color. And then we will also look at H2O. Which substance on the right-hand side, on your product side, looks exactly the same, not exactly, but very similar, but differs with an H+, and that's your hydronium ions. So then the acid, sorry, let me maybe keep the colors similar so that we can identify them more easily. So your acid will become a conjugate base. And then here we know that water is acting as a base because it received a proton, and that will then become your hydronium ion. So your base then has a conjugate acid as a pair. Right. I am going to do this example with us as well. So if we look at this one, we know that we've got HCl and water. We know that HCl is the acid, H plus is donated or transferred to your base. Right, so if you have HCl minus your H plus, you know that you'll be left with chloride ions and you will be left with hydronium ions. And now easy peasy, because we've just done it. Which ones are your acid-base conjugate pairs? HCl and Cl minus, acid and conjugate base on the product side, and then our base and our conjugate acid. So those two are paired up and these two are paired up. Right, so really not the most challenging concept, but it seems even with the matrics, in the exams, we rush and then we actually can't remember what an acid-base conjugate pair is, and those are marks that we can easily get. Righty, so as we move on, and these are quite important little, I want to say definitions, but words and phrases that we are revisiting if you've done this already at school. So ampholytic and amphoteric substances. Now, this is a substance that can act as both an acid or as a base. We've just dealt with one. The most common example is water. Depending on what water is reacting with, water can react or act as both an acid or a base, even in the same reaction. And that is where eventually, I think in grade 12, you get to a section where you look at the autoionization of water, of how water can react with itself as an acid and a base, which is quite confusing at times. All right, so let's go. Amphoteric substances can donate or accept protons. It all depends on, I always say it's all relative to what they are reacting with. So if we look at the example here, and then we'll also do one. If we look at the example that is here in front of us, you see if we give you HSO4, which we dealt with earlier in the sulfuric acid reaction a little bit earlier when we did the steps, if it acts as an acid, it will donate a proton, and your product will have your polyatomic ion without the hydrogen bit because it donated it to water, which acted as a base. However, if we tell you that in this reaction, you have to not pretend, it does actually act as a base, you need to write the product or you need to write the full reaction, then we know water is then acting as the acid. If this is my base, water can then act as the acid and the other substance can act as the base and then receive the proton. And if that substance HSO4 minus receives one hydrogen, then we know H2. And if it was negative and it gained a positive charge, it's then neutral, and hence, therefore, there is no charge that you will see. All right, so quite a nice little example that you have there. We're definitely not going to do both of these, but just to show you that when we look at water, and I see now that at least I gave acid and base example, we know that HCl is an acid, and therefore water will receive the proton. I'm not going to do the whole reaction. Let's focus on the little bit that is important. The fact that water can in this reaction receive, we know that it will then become H3O plus hydronium ion, which we've dealt with. But in the second example, excuse me, you'll now see, or you also have an acid. Silly. Let me just give a different example. I apologize profusely. Let's do NH3. There we go. I think that's what I was supposed to do. I was in thought earlier. So NH3 is a base called ammonia, if you didn't know. So you'll see these lessons, sometimes we learn something very quickly, which we might not have known. Ammonia has a base. The base reacts with water. Now, some of you might go, whoa, why is water written as part of my reaction? all bases should dissociate, but all bases don't dissociate. And I'll explain that in a couple. All right, so in this reaction, water is now acting as the acid because the other substance is already a base. And you don't have base-base reactions or acid-acid reactions, acid-base reactions. Okay, so what must happen is a base is a proton acceptor, and therefore it's going to become or form NH4 plus because it gained the positive charge. And then you'll see that H2O will now form OH minus. Be very careful because we always think it's HO and then a negative sign, but we notice OH minus, which is hydroxide. All right. Well done. We're going through this quite quickly because it is small little concepts that eventually they will form part of the bigger picture. So please, if you've got any questions, please stop me and ask as we go. Right. I just want to take a moment to look at the difference between concentrated and dilute. And then we will look at strong versus weak, because every year there are students that get confused, and we need to make sure that we actually understand the difference between these. There are four actually, so concentrated and dilute, and then strong versus weak, and then concentrated versus strong, so that we actually know what the difference is. So I'm going to look at the notes and then I'll refer to an example as well. So concentrated, we know that you know C is N over V. So if the volume stays the same and we add more mole, then the concentration will increase. If you're not entirely sure where I'm getting that from, C is N over V. You'll see that these two beakers, the volume is the same for both. So the volume to the left is the volume to the right. Well, I'm assuming because the beakers are similar size, but let's say that they are. If your volume stays constant, I always just make a little one for myself if the volume stays constant. But if the volume is constant and I'm adding more of one substance, indirectly you're adding more mole. If the mole then increases, it means that the concentration would also increase. Okay, because mole and concentration, if the volume stays the same, then they are directly proportional, which means if the one increases, the other one must increase as well. All right, so when you talk about concentrated, don't worry about the strong, weak for now. We're just focusing on concentrated versus dilute. If a substance is concentrated, it means that in a specific volume, there is a lot of that substance in that volume and diluted with very little water, for instance. Okay. I have done a little diagram. I cannot draw to save my life. So I see that Rotendo, there's a question, why does the base not dissociate in the previous example? I'm crossing my fingers and I promise you I am not just shoving it to the side. We are going to look at that example in literally 2 to 3 minutes. I will explain the difference between ionization, dissociation, and why that particular base did not dissociate. Okay, so I even have little notes here of things that I need to remember, and that example is in here. I just want to get to the notes where you can actually see the example in front. Okay, so I will remember, right? So just back to concentration. If we look at concentration, that is the proportion of a substance in a mixture. So proportion or ratio. So if you've got a beaker, I don't even have one here. Usually I've got like little pieces of equipment or examples I can show you. But if you've got a beaker, and let's say it is 100 ml, so that's why I drew them. So you've got 100 ml in total. And now let's say that the top bit is water and the bottom bit is any form of a substance, let's say HCl, right? Don't worry about how they ionize and dissociate and all of those beautiful things. Just focus on the total amount in that volume. All right. So a lot of hydrochloric acid, a little bit of water. This is concentrated because it has not been diluted that much. There's not a lot of water. The same 100 ml, if you look at the second example, if you still have 100 ml, so your volume has to stay the same. But what do you see? So second beaker, now we've got a lot of water and only a little bit of HCl. What does that tell us? You have diluted it more. So if you've got a lot of substance, a little bit of water, it is very concentrated. So the number of particles of that substance in that beaker or in that volume is very high. So the number of particles, so the proportion of the substance in the mixture. So the substance, let's say that this is our substance. the proportion of that to water is a lot of that substance, HCl, and a little bit of water. Whereas in the other example, to the right-hand side, you'll see that you've got a lot of water and very little acid. Please give me 2 seconds. I just see that my power plug is off. I just want to plug it in. Otherwise, we're going to have a problem in 2 seconds. Apologies. There we go. Cool. So when you look at these examples, it is incredibly important for all of us, whether it's grade 11 or moving into grade 12, to always focus on the fact that the volume must stay the same. The moment you mix or change the volumes, then it's quite difficult because then there's not a comparison. So I always keep 100 mils. One has a lot of a substance. Think of Oros or any form of a cool drink that you need to dilute, Energade, whatever it is. If you have a very strong, if you like it to taste very strong, then obviously you need a little bit of water and a lot of substance. Whereas if you like it to be more diluted, so please note that I said strong instead of concentrated. So if you like it concentrated, then a lot of substance. But if you like it diluted and a little bit more watery or watered down, then the water must increase, but your container stays the same size. Right, so you can't change the volume when you look at concentrated and dilute. All right. So that is our big difference between concentrated and dilute. And in the same breath, I'm also going to look at these two terms. And here you'll see I'm going to slow down, literally in my speech and also in my writing. This is a concept that could potentially be new to you. Maybe it's the first time in your high school career that you've heard the word strong. We talk about a strong acid on the pH scale. It's very low on the pH scale, but we never actually understand why some acids or why some substances are very low on the pH scale and others are closer to 7, but they are both acidic. Okay, so we've just dealt with concentrated. When you look at strong, I want to say that strong versus weak is almost the way in which the acid will react or the way in which the base will react. So here, and I think this will retain, or this is where I will now start answering your question as well. Okay. So I'm going to just move to the side. And this is why I asked you guys to have pen and paper. And maybe your teacher explained it this way, and then I'm incredibly happy. But sometimes we just refer to, in the sections, we just refer to acids and bases, but we don't really look at why they undergo certain changes. So I'm going to start by looking at the acids. And I'm just going to stick to the examples we know. All right, we will get to the unknowns a little bit later. The moment I say HNO3, we know it's nitric acid. How would you know, and this is where my students also, and they don't know, how would you know whether you must write plus H2O and then have products? Or how would you know when to write H2O, water, on your arrow where it doesn't participate in your reaction? Because now we've got two terms or two phrases or two words that we have hopefully been exposed to. And the first one is dissociation. Also just double check my spelling. Dissociation, and the second one, in any order, one is not more important than the other, and ionization. All right. Ionization is the process where, and you'll see that I'm going to keep on going on this document. Ionization is the process where covalent bonds, and so when we started, I reminded you that intermolecular forces, if some of you have looked at it, and equilibrium could come in handy, right? So covalent bonds undergo ionization. That's the process that they undergo. But what is ionization? It's when they react with water. I'm going to write H2O. So ionization is the process, because you've got two. One is where water is written as part of your equation. And remember, if a substance is visible in the reactants, it must be accounted for on your product side, which means you must be able to balance your equation. It might look different, grade 8 and 9 chemistry. You know, when you write an equation, the products might look different, But if you've got one potassium to the left, you must have a one potassium atom to the right. And if you've got NO3, only one of those, of each of the elements or whatever it is, how you're counting to the left, then you must have all of that to the right. So ionization is when a covalent bond reacts with water. And this, and I'll keep on just, highlighting in colors so that we can keep them together. Ionization is when a covalent bond reacts with water. Why is HNO3 a covalent bond? Let's remind ourselves, what is a covalent bond? A covalent bond is where you've got two nonmetals. That's how we were taught when we did intramolecular bonds, if you've done that before. So we're used to saying two nonmetals, but it could also be a nonmetal attached to a polyatomic ion. Okay, so I am slowing down, polyatomic ion, let me just spell correctly. I am slowing down and almost just pressing pause on the acids and bases theory and just revisiting what is a covalent bond? How do I identify them? Oh, and if it's a covalent bond, it undergoes the process of ionization, and ionization is when it reacts with water. So I am a creature of habit, which means you do things the same all the time. So I will stick to color. So HNO3, hydrogen, yes, it is to the left of the periodic table, but it is a non-metal. It reacts as a non-metal. So HNO3 is a covalent bond, yes. So it will react with water, which means you must have water as part of your equation. And whenever you've got two substances as your reactants, now some things should maybe start making more sense for some of you. If not, hang in there, we've got the whole afternoon. But if you've got two substances on your reactant side, now a proton can be transferred. If you only have one substance and water is written on top of the arrow, then it can't transfer the hydrogen, it can't donate, it can't accept, because where does that proton go? Right, water, if written on the arrow, it means it's just present, it's just there, it's just a vessel. All right, so when you look at this, remind ourselves that water is written as part of the equation. So what will our products be? And so this page will be very full with written notes, but it is important just to revisit this concept. So we know that this is an acid, nitric acid, so it will donate a proton. And what will we be left with? NO3 minus and H3O plus. So this is an example of ionization. So please don't fall trap to just saying, oh, what is ionization? It's the reaction where acids are present. It is coincidentally, well, not coincidentally, but it is because all acids, if I have to show you the acids that we've now worked with today, H2SO4, hydrogen attached to, which is a nonmetal, attached to a polyatomic ion, covalent, and therefore sulfuric acid will also react with water. So it will be written as part of the equation. HCl, nonmetal, halogen, nonmetal, covalent, it will react with water. I'm going to just throw in one or two more that you might not have crossed paths with. Let's look at the one that we did actually cross paths with earlier. Phosphoric, H3PO4. No matter how many hydrogen atoms there are in that little bond, it's covalent because it's non-metal and a polyatomic ion. Now, yet again, it will react with water, H2O. My last one, because I think you are getting the idea, is HF, hydrofluoric acid, hydrogen fluoride. Yes, it is an acid because it's hydrogen attached to a halogen. Non-metal, it reacts with water. And that's why all acids will undergo ionization. Okay, so just to refer back to Rotendo's question, we looked at ammonia a couple of minutes ago, NH3, which is a base, and we know bases as to undergo dissociation where they merely break up into their ions. Why did it not? So let's look at that. So that's our notes for the acids, right? I'm going to scroll across and we're going to start with the bases. If you think of bases, So I'm sorry if some of you are comfortable with this theory, but every year I realize that we just glance over it and we actually assume that you guys know it. We need to revisit this. All right, so if I say NaOH, so if you need to be reminded of what a base is, a base, strong bases, so I'm going to write ACE-B for strong bases. They are group 1 metals. So much theory for this section as well. So therefore, I'm going through it quite thoroughly. So group 1 metals attached to a hydroxide. Okay. Then weak bases. When you've got carbonates, so CO3, 2 minus attached to a metal. When you've got group 2 metals, attached to hydroxide. So the one example that I'm just going to sort of throw out there is magnesium hydroxide. And now let's revisit writing a formula. Magnesium is in group 2, which gives it a valency of 2+. Hydroxide, OH, polyatomic ion, 1-. So 2+, 1-, there must be 2 hydroxides, and therefore you have to have your brackets. Okay, so side notes. And then another weak base, which has to be mentioned to you, you won't just know it, magically, is NH3. And this is ammonia, and that's the one that we looked at earlier. All right, so let's use the example that I've got here, and that is NaOH, right? Firstly, let's do exactly the same that we did with our acids, and we're going to make a couple of notes. Just want different colors so that it can stand out. All right, bases. What type of bond, so intramolecularly, what type of bond do you have when you look at bases? So that is a metal, a cation, and a polyatomic ion, a non-metal, or then an anion. So what do we call the bonds that are formed when you've got a cation and an anion? Those are called ionic bonds. Right. So any base, and I said I'll stick to colors, so let's do it. Any base that consists of an ionic bond will undergo the process of dissociation. And what is dissociation? The breaking up. I'm doing this because this is not a definition. I'm just explaining. Please note, whenever I do little bunny ears, it means you need to go and study the definition. I'm just explaining and paraphrasing. So any base that is an ionic bond will undergo dissociation. And what is dissociation? It is the breaking up of an ionic bond into its ions in the presence of water, but not reacting with water. So NaOH, in the presence of water, so guys, it dissolves in water. So NaOH, I worked with it earlier this week in my lab. It's little, it almost looks like little pearls, but they've got a flat bottom. So flat bottom, and then like a rounded little structure, and they are a whitish, off-whitish color. And if you add that to water, it takes quite a while, but then eventually if you stir or if you swirl your test tube or whatever it might be, it dissolves. So what happens when an ionic bond undergoes dissociation? It breaks up into its ions. And now ask yourself, water is on top of the arrow, written on the arrow, which means in the presence of my base dissolved to break up into its ions. Do I have to account for water on my product side? No. And I don't fall trap to go, oh, but there's an OH. Where did that come from? Merely from your base. It is the Na plus ion, and it is the OH minus ion. Your cation and your anion broken up in the presence of water. So why does NH3, so all bases, let me just mention that, all bases that consist of a cation and an anion will undergo the process of dissociation. In the presence of water, break up into their cation and their anion. Why did, and this is where our next color will kick in, why did NH3, ammonia, not undergo dissociation? You didn't write water on top of the arrow, we wrote it as part of the reaction. So Rotendo, here you go, just for you. So NH3, what type of intramolecular bond or what type of bond is present? Nitrogen is a nonmetal, hydrogen is a nonmetal. So this is a covalent bond. And covalent bonds, and I'll scroll across, covalent bonds do not undergo dissociation, where the arrow and water are written on top of one another or above one another. We know the process of ionization, and forget about the word acids. We just know that all acids will ionize. But ionization is the process where a covalent bond reacts with water, and there's a transfer of a hydrogen or a proton. So let's look at this example. NH3, you don't write it arrow with water on top because that is dissociation for ionic bonds. So no to that. You will write NH3 plus water. And now we know it is a base. A base is a proton acceptor. So your proton will move that way. You're going to be left with I say left with, it's going to form. Left with sounds, oh, this is what I'm left with. It will then form, apologies, NH4. And if you do take that proton away from water, you're going to be left with OH minus, which is your hydroxide ion. So in a very long explanation, but a very necessary one, I think. Rotendo, if you can maybe just give a thumbs up or a high five or just something, if you do understand, if it does make sense. Why does the base that we looked at, which is NH3, why does that one not undergo dissociation as such? Why did we write it as part of the equation plus water? It is a covalent bond, and covalent bonds, what do we know? Non-metal, non-metal, and therefore it must undergo the process of ionization. But because it is a base and the word dissociation we usually put together, and ionization and acid. All right, cool, I see a thumbs up. All right, if anyone else just learned something new, maybe just to also make sure that you're awake, a high five, a thumbs up, any little emoji which is acceptable, that would be great, just so that I know I'm not just talking to myself. It's always interesting to learn something new. Yay! Woohoo! Okay, 5 people learned something new. Great. Okay, so I have to be honest, for years of teaching, I always went acid-base, but remember the one base that is the exception. But I failed to teach the students why it is the exception. And so from 2 years ago, I thought, hey, let's do that. All right, so let's quickly just refer to our notes, and then it's almost time to take a little bit of a break because it's already been almost 50 minutes. All right. So the strength of an acid and a base refers to the ability of a substance to either ionize or dissociate. So strong acids, which is that list of 3. So I'm going to give them to you again. HCl, let's recap. H2, I hope in your room you're saying it out loud. And HNO3. Okay, I'm quite an audible learner, so there we go. A strong acid will ionize completely. Ionize completely means, and if you have done equilibrium, I actually want to ask anyone who has done equilibrium in their school, because that's also important. High five, thumbs up, smiley face, just something if you have done something regarding equilibrium, because that's quite important as well. Or rates, that could also go. Okay, a couple of you. All right. So when we talk about, please note if you haven't, you can still do acids and bases, all right? A strong acid will ionize completely, which means the reaction that we see in front of us here, hydrochloric acid reacting with water, single arrow. A single arrow means the reaction can only take place from left to right. And that's how many of you know reactions. You're like, what? There's a second option. But if you've done equilibrium, and when you do get to equilibrium, then you'll feel quite chuffed with yourself in class for knowing that ahead of your mates. But if it is a single arrow, it means it can only be written and read and take place from left to right. Reactants will become those products or will form those products. The moment that you see, and look here at the bottom of our notes here, the moment that you see a double arrow, it means that the reaction can go forward. And if you've got a little bit too much or enough product, then the reverse can start happening. And so that is just back and forth, back and forth. So when we look at a reaction, if there is a single arrow, it means that it only takes place from left to right, which must tell us what? If you started with a lot of reactants, doesn't matter what reactant, don't even think of a specific reaction, just think reactant. When a reaction starts, you've got a lot of reactant, but very little product. And then as the reaction takes place, what are we doing? We're using our reactants, so they are becoming less, and your product is becoming more. And so if it's a forward reaction, a single arrow, it means that you have got the smallest value of reactant, but a lot of product. And what will that then tell us? The reaction was very sufficient or efficient. It was very successful because we've got a lot of product, very little reactant, and therefore a single arrow. So strong acids can only go one way. They ionize completely. So what I always just encourage my students to do is to say a lot of product and very little reactant, not no reactant, because we've done in grade 10, we've done limiting and reagents in excess, right? So it's not as if you use everything up. We never say that your reactants are used up, but they are used to such an extent that you've got a lot of product and very little reactant. So that is a single arrow. Okay, so when we talk about strong acids, why are these three acids examples of strong acids? Because they are all written with a single arrow, which means they ionize completely. A lot of ions are present. Okay, and what type of ions? When we look at an acid, and that is something that I haven't mentioned, and we'll move into that now, hydronium ions is the proof of a presence of an acid. So whenever you see hydronium ions, you know, ooh, okay, acidic. Hydronium and acids, they go together. All right, and now also the flip is true, or the flip side is true. Whenever you look at a weak acid, it's the way in which they react. A weak acid, yeah, a little bit of reactant, a little bit of product, a little bit of both. It's not completely ionized. Ionized completely means you've got a little reactant. So the double arrow must tell us, even if you haven't done equilibrium yet, a double arrow tells us that you've got product and reactant present. It's not really leaning towards one side. Both are present, not always in equal amounts. Don't worry about that. But if you see a double arrow, that tells us that it only ionizes partially. You can also say that it doesn't ionize completely. And then just before we take a break, what are the ions that we know that are present? So these are still acids that we are looking at. So hydronium ions are the acids that are present whenever you work with an acid. Right. When we look at the strength of bases, and this is where we will take a break just after this, because now we've done strength. So a strong base, what can you tell me? Bases dissociate because they dissolve in water. Water is written on top of the arrow. Okay. So bases that are strong, group 1 attached to a hydroxide. So LiOH, NaOH, KOH. So lithium, sodium, potassium. I don't think they're going to get to rubidium, cesium, and francium. But if they do, don't stress. Find them on your periodic table. But LiOH, NaOH, KOH, they dissolve in water. Single arrow. So you'll see strong bases, single arrow, a lot of hydronium ions. So the hydroxide ions. So the concentration of hydroxide ions, it's very, very high because there's a lot of product. The moment that you look at a weak base will only dissociate partially, which means double arrow. Yeah, you still have hydroxide ions. They're still there. Yeah, but there's a little bit. You can somewhere hear the tone of voice. There's a bit of both. Okay, so single arrow, strong acid or base, a lot of product. Weak acid or base, double arrow, there's reactant and product. And therefore you can say that they ionize. If it's an acid, ionizes partially or completely, or if it's a base, dissociates completely or partially. Right. Sure, you've been sitting for 55 minutes. What we're going to do is, it is 15:24. If we can... All right, so we've just looked at the difference between strong and weak, and that in comparison with concentrated and dilute. And so I'm just going to bring us all on the same page. Concentrated and dilute is where you refer to the same total amount or volume, but the ratio of the substance to water or whatever it is dissolved in is either a big ratio or there's a big difference or they are very close together. So a lot of acid, very little water would be concentrated, whereas a lot of water and little whatever other substance would be dilute. Okay. Strong and weak is how these substances react when they are part of an equation. So for instance, if you have your base that dissociates, if it is a strong base, Single arrow dissociates completely, a lot of product. If it is a weak base, dissociates partially. Present in that equation, you'll still have some reactants and some products. And the same with your weak acid, I've just done the base. A weak acid will ionize partially. So you'll have some product, some reactant. So double arrows for weak and single arrow for strong. With that in mind, we're going to start looking at the influence of acid and base strength with regards to reaction rates. So please don't think that it's any different now because it's the strength of an acid and a base. Right? But on reaction rate, what happens is the reaction rate increases as the strength of the acid or the base increases. So technically, if you think about it, if you've got a stronger acid or base, it is a higher concentration of the ions that are formed. And we know that these ions could be either hydronium or hydroxide. So I'll write both of them here, just for those who are following step by step. Sorry for that plus being all weird, right? So if it's a stronger acid or base, you've got a really, really large amount or concentration of your ions that are formed, right? And therefore we know that that will result in an increased arrow up is increased, all right? Just because my writing, it's going to take us forever. So an increased rate of reaction. The same thing with the weak. The weak would just be the inverse or the opposite. Weak would be a low concentration of hydronium or hydroxide ions, and therefore the rate would then be lower or decreased. When we think of conductivity, or when we address conductivity, it's the ability of a substance to conduct electricity or to transfer electrons or current, right? And so here, it's very important to know if you've got your single arrow, we said that would be a strong acid, SA is strong acid, or a strong base, right? That would be single arrow. And we know that that will mean a high concentration of hydronium or hydroxide ions, right? If it is a double arrow, so a weak acid or a weak base, then we know that the concentration, so a high concentration for strong, weak will be a low concentration of those ions being formed. And what is conductivity? Firstly, certain substances cannot conduct electricity. Covalent bonds cannot conduct electricity. However, ionic bonds, so we are now reverting and going back to our intermolecular forces or types of bonds. If you look at NaOH, what do we know? It consists of Na ions, so sodium ions, and hydroxide ions. And what do we know about ionic substances? They are good conductors, or they can conduct electricity when dissolved in water. Why? Because they form free ions. So here we go. If it is a strong acid or a strong base, a lot of ions are present, single arrow, therefore good conductor. If it is a weak, opposite a weak arrow, a weak acid or a weak base, there's a double arrow, which means that you've got reactant and product. So, you know, not equal amounts, but they're all present. So it's not that it is not a conductor, but it is not as great a conductor as a strong acid or a strong base would be. So it is a weaker conductor, or not as great as a conductor would be if it was strong. Right, so therefore, the influence of acid and base strength is important to understand with regards to conductivity. Right, remember that. Here's a beautiful list, which I'm definitely not going to go through every single substance, but just to point out that it should not come to a surprise to you. I always tell my students, know your strong acids. SA for today is strong acid. Know your strong bases. SB for today is strong base. Don't go and study all of the weak acids and all of the weak bases. Know which ones are strong. There are 3 acids: hydrochloric, sulfuric, and nitric in any order. And then your strong bases will be a group 1 metal with a hydroxide. So I see they've got sodium hydroxide and potassium hydroxide. Any other substance that in an exam they label as an acid or a base must then be weak. Okay, there's no catch. There isn't like a sneaky little strong base or strong acid that's going to come along. Those are your 3 strong acids, and those are your 2 of the possible 3 or 4 strong bases. And that is it. Any other substance is then a weak acid or a weak base. So please don't spend hours and hours studying that table. Rather just know your strong ones, because there are only a couple to remember. Right. It's not about working harder, it's about working smarter, I always say. So now some of you will get excited because this reminds you of prep school, the pH scale. The pH scale goes all the way from 0 to 14. And we know that acidic substances are less than 7, basic substances more than 7, and then neutral close to 7. Neutral, yes, is 7 on the dot, but when we talk about a substance like water, very often you will have drinking water that is not 7 on the dot. So please note, neutral is 7 on the dot, but water, which could be a neutral substance, might not always be 7 on the dot. And how I explain this to my students is the following. We know that acids, what is the ion that is present when we want to prove that an acid is there? We know that that is hydronium ions. For a base, it is hydroxide ions. So if your concentration of the substance that you are working with has a very high arrow up, a very high concentration of hydronium ions, it is a very strong acid, single arrow. It's a strong acid if the hydronium ion concentration is very high. Why? Because it's forming a lot, little reactant, a lot of product. So if your hydronium ion of the substance, if the hydronium concentration is very high, it means that it is a strong acid. And where will the strong acids fit on your pH scale? We know that they will be further down, I say to the bottom, but it's more to the left, but to the lower digits. Okay, so 1 to 3 maybe. Whereas an acid with a double arrow is still an acid, it's still below 7, but what do you know? That it is not strong, it ionizes partially, so your hydronium ion concentration will not be that much. So what is it that we need to identify here? If hydronium ion concentration increases, your pH will decrease because a strong acid is very low on the pH scale. Whereas, I want to say the opposite, but on the other side of the scale, if we look at bases, bases have hydroxide ions present. If you have a lot of hydroxide ions, the concentration is very high. It means it's a strong base. And so where would that be placed on your pH scale? Closer to your higher digits. It is a beta or a stronger base. So the easy way to remember is if it's a strong acid or base, it will be closer to the outskirts or to the extremities. Whereas if it's a weak acid or base, it will be closer to the center. And if it's neutral, it will be on the dot, 7. All right. So these two little sentences I have explained, and so you can most definitely read through them. But remember, the concentration that increases, that is the substance that you are working with. All right. I want to get to one of the sections where I always say that it is sit on your chair and study, unfortunately. And then you do have to understand balancing. But there are 4 equations or 4 reactions that we're going to look at now. We refer to them as proteolytic reactions, or we can also call them acid-base reactions. And so why would they be called proteolytic? It's the transfer of a proton, right? But in some cases, you'll see it's not just the easy, oh, where does the H go? Where does your hydrogen ion or your proton go? Okay, so these are actual reactions where you've got an acid and a base, and they are set products that you will always have. And we need to understand, or we need to learn rather, and then understand what happens with these reactions. So I'm going to number them, if that is okay with you. This is going to be reaction 1, acid and metal. Reaction 2, I will look at them in detail now, but let me number them first. All right. So you will see every time that there's a little arrow here at the top, it means that something else is coming. There's an insert, or wait for it. Wait, there's more, like infomercials. But let's look at them first. In your notes, you'll see whenever you've got an acid, we've now dealt with acids, HCl, HNO3, H2SO4, strong ones, and then there's a whole list of weak ones. An acid plus a metal, you'll see that some textbooks and some websites, be very careful with your resources, but some textbooks and websites refer to it as an active metal, which is just a metal by itself. Right, so metal by itself. So we know metals to be copper, zinc. Really, we do know quite a lot of metals. Let's not put silver in there because we're going to look at the reactivity table. All of those beautiful things. Let's put cobalt in there. Right. Whenever you've got an acid plus a metal, this must be your product. you must have salt, and be very careful. We know salt to be NaCl. That is a type of salt. Household name is table salt, but sodium chloride is a type of salt. So I'm going to slow down and explain what a salt is now. But you must always have salt and hydrogen. And if you've been in any of my sessions, I apologize, but if you've been in any of my sessions, I always remind you of the following. So apologies if you have, and you've heard this now a couple of times. Hydrogen and a couple of other substances, or let's rather refer to them as elements, cannot just be this hydrogen when you write it out. It's not just H, it must be H2. And so why? We refer to these as diatomic molecules. Di, two, atomic, two of the same atoms forming a molecule. And what do we know? Molecules are formed when non-metals form a bond. Right. So here is your little, I want to say, acronym or rhyme. You can make up your own, but this is mine from high school that I was taught. Have no fear of ice cold beverages. All right. So all of these are called diatomic molecules. And why am I even looking at this? Because if ever you get a word equation and we just say salt plus hydrogen, please write a balanced chemical equation. Then you can't just write H, H2. Okay, they do not exist, I want to say, in nature or naturally by themselves. They are diatomic molecules. So yes, on the periodic table, they're going to be singular because that refers to one atom of that element. But hydrogen, if ever you see, forms chlorine gas. Cl2. Okay, so have no fear of ice cold beverages. All right, so what I'm going to do is I'm going to just look at the rules. Let's call them rules. Those four that are numbered, and then we're going to practice and try a couple. So whenever you've got an acid that reacts with a metal, these are the products that you must have: salt and hydrogen. And now some of you might ask, what is a salt? And we will get there. I will cross my fingers and remember. The second rule is whenever you see an acid that reacts with a metal hydroxide, and we know by now that hydroxide is OH minus. So based on the valency of your metal, you might have to bracket your hydroxide with a subscript. Okay, so your acid added to a metal hydroxide will always give you salt. And we will explain what a salt is and how you form a salt, and water. This is a rule. So if we tell you that HCl, oh, they have an example here. Sulfuric acid reacts with magnesium hydroxide. This is an acid. There we go. And this is a metal hydroxide. What must my products always be? You must have salt and water. And then the important part is then you need to balance, and we will practice a couple as well. Before we look at what a salt is, let's look at the third reaction, which you need to sit on a chair and study. I am sorry. An acid reacting with a metal oxide. Oxide, when you wrote formulas, you know that the surname bit, due to the lack of better words, the second part of your substance is the metal is the first bit, name stays the same. The second bit, oxide, nitride, phosphide, chloride, bromide, iodide, we can continue for a while. That comes from your periodic table and the element, which is a non-metal. So oxide comes from oxygen. Right, so whenever you've got an acid that reacts with a metal attached to an oxygen atom, so let's use the example, I know they've got magnesium oxide, but something like copper 2 oxide can also go. You will also have salt and water. So rule 2 and 3, the hydroxide and the oxide, they have exactly the same products, salt and water. But because the one is oxide only and the other one is hydroxide, OH, your balancing might just have to be different. All right. And then the fourth rule, and then we will start looking at what salts are. Whenever you've got an acid that reacts with a metal carbonate, and we know carbonate, and I know it is typed there, CO3 charge 2 minus, polyatomic ion. Whenever you've got an acid that reacts with a metal carbonate, your product will be, and now it is slightly different, it's salt and water. And because of the CO3 present, you have to account for every reactant in your product. So you can't just have salt and water. There's a carbonate on your reactant side. So carbon dioxide will form. And you will have to balance it out. Okay, so there are examples underneath each of these rules. I definitely don't just want to read through them, but I would, if I were you, after the session or in the next couple of days, just ensure that you understand where your reactants go after I've explained and what products will form. Here at the bottom, they say, the ionic salt is made up of, and you'll see in all of these examples, they're hypothetical examples, which is great, but they sometimes confuse me. So A minus from the acid, so the negative part of your acid, and then the metal or the positive, the cation from your base. So I'll repeat, how do we form salt? And remember, salt here, we don't just refer to NaCl, that is a type of salt. See salt as a little heading, and then how do we form salts, plural? A salt is made up from the anion from your acid, so you can for yourself write that in there, the anion of your acid plus the cation of your base. So what I usually do, and you will see as we go across here, what is a salt? You see, I was prepped. But what a salt is, and you can either go by that rule where you remember that it's the anion of your acid and the cation of your base. How I usually just teach it, and it is always the same, there are no exceptions, is when you want to form a salt, remove the hydrogen bit from your acid and just plug in your metal or your cation from your base. It's exactly the same rule. We're just using different wording and maybe a bit of a picture. So if I'm asking you to show what salt would be formed when hydrochloric acid and sodium hydroxide react, firstly, what rule are you busy with? 1, 2, 3, or 4? Numbering is really irrelevant, but which rule? This is an acid that reacts with sodium. Na is a metal hydroxide. And so I know them off by heart, but just to show you, acid and metal hydroxide. So now you have to go, acid and metal hydroxide. Okay, I know now it must give me a salt and water, but please know it off by heart. We can't in an exam now sit and struggle and not remember. So salt and water. And how do we form a salt? You remove the hydrogen from your acid. This is my way of explaining it. Remove the hydrogen, any form of a hydrogen. If there's 2, if there's 1, you remove your hydrogen component and you're left with a Cl. All right, so I'm just going to show you how you write your formula. You're left with Cl minus, okay? And then you replace the H, the hydrogen component, with your base metal or with your base cation, which is Na. And what ion is it? Na plus. So why am I looking at the ions? Because if you write the formula, the valency is important. So this is quite an easy example. I think that's why I chose it. So it is NaCl. So what could you potentially see? What could a salt be? A group 1 metal, group 2 metal, a metal attached to a halogen, or a metal attached to a polyatomic ion could potentially then be a salt. And we know that we need water as part of our reaction. And then you just need to check whether you have to balance it out. And I'm going to do the old school way. There's 1 hydrogen to the left, and we've, 1 hydrogen and a hydrogen there, apologies, 2 hydrogen atoms to the left, 1 chlorine to the left, 1 sodium, and 1 oxygen. And then if you look to the right on your product side, I know this is a grade 9 way, but some of us really struggle with balancing. And so I want to show you how quickly you can do this. So 2 hydrogen was sorted, 1 chlorine sorted, sodium, sodium, oxygen, oxygen. It is balanced. So this reaction is already balanced. So you do not have to have any coefficients. Right, so that is what a salt is. So what I want to just show you is that I have added this. You'll see that this is not in your slides. I sometimes just add what I use at school. So you can either have the rules typed out. I just give this to my students and I just remind them that there are a couple of reactions, and you'll see that we have not dealt with the bottom one today. I think that that is one that we do with our matric students only later. So here is rule 1. I call them rules, but reactions. What will you see? The products are always fixed. So you need to sit on chair and study. So acid and an active metal will give you salt, and hydrogen, and remember that it is H2. And please remember, and we're going to do redox reactions still in the session, rather, and you'll see that there will be time. But a redox reaction is where partners have been swapped and charges have changed, all right? And here you'll see that this is a proper acid and base reaction, because what is a base? A metal oxide, metal hydroxide. Okay, so whenever you've got an acid and a metal oxide, you'll have salt and water. The next one, salt and water, exactly the same. And the trick is to remember with your carbonate that you must have carbon dioxide, CO2, as a product. Apologies. CO2 must then be a product. Okay, so I just wanted to show you, you can also just summarize it for yourself. It doesn't have to be the typed out with an example, and you don't always have to use hypothetical acids and bases. I think it's really smart to use hypothetical acids and bases. So H is your hydroxide, but then the A means any form of an acid at the end. But for me, sometimes I just enjoy seeing the actual example. Right, I'm quickly just going to look at one of these. Let's not do both. Just for time, I'm going to look at one of these. If you've got pen and paper with you, I'll give you a couple of seconds, but let's do this together. Write a balanced chemical equation for the following reactions. Let's do number one. So a hydrochloric acid and copper oxide. So first things first, we must know that hydrochloric acid is HCl, and then copper 2 oxide, just for those who are not comfortable with writing formulae. Copper 2, the Roman numeral means that the valency is 2+. It's a metal, so it's a cation. Oxide comes from oxygen. We know that it is O2-, and so therefore it will be one of each, because the valencies are equal but opposite in charge, so CuO. If that was very quick, just go and revise writing a formula. It's very important. It follows you all the way up to matric. So now, what do we know? It is a metal oxide. The rule for metal oxide says that I must have a salt and water. Okay, so if you want to for yourself, the first few lessons when you try and practice this, write down what you should have. And now we know. How do I form a salt? I remove the hydrogen from my acid and I replace it with a cation from my other substance, from your metal oxide. So now you're going to have Cu, and now be very careful, which is 2+, and Cl, 1-. So you can't just go CuCl, 2+, 1-, so you need 2 chloride ions. So just be very careful when you do that. So it is CuCl2 and H2O. And now we have to check whether this is balanced. Let me just remove the little cross so that you know there is an actual hydrogen there. All right, so now you have to make sure that it is balanced. And by the looks of it, we're going to need 1 hydrogen atom this side, 2 chlorine, 1 copper, 1 copper. And we're going to have, I did this one earlier just to double check, then I think that is balanced. CuO, yeah, there we go. So you merely had to double up the first little substance, right? So whenever you write these reactions, we are testing whether you know your rules, or those 4 little steps or 4 little examples. So it is important that you know them. Please don't ever enter a test or an exam without having studied them. And also not just for a test and exam, lessons become easier if we are prepped. Right, I promise you, trust, it does. All right, we're going to look at hydrolysis of salts. This is a section or a subsection where many students struggle to understand how we know which ion has to be part of your hydrolysis reaction. Let's look at the basics of what hydrolysis is before we actually do that. So when you look at the term hydrolysis and the hydrolysis of salts, especially, it means that an ion of your salt reacts with water. So why do we do this? So my students always ask, okay, it's great to know what hydrolysis is, here's the definition, but hydrolysis is when the ion of, or an ion of a salt reacts with water. You can be asked ultimately at the end when a taste exam, etc., you could be asked, is the following salt acidic, basic, or neutral? And if you don't know how to apply hydrolysis, then it becomes quite tricky. Okay, so I have simplified it for myself when I started teaching a couple of years ago, 12 to be exact, but I simplified it to find a way that I can explain and express and just come across in a manner that would be maybe relatable to students. So let's try it and let's see how it goes. If you look at the definition, hydrolysis is an ion of a salt that reacts with water. Okay. So I've got a beautiful example here for us and my cloud just to remind us what hydrolysis is, the ion of your salt that reacts with water. For yourself, if you would like to, just add the following. It's not an addition to your definition. That is the definition, an ion of a salt reacting with water. But how do you know which ion? Because a salt has two ions. It has a cation and an anion. And if the wrong one reacts, you might get to the wrong answer, and therefore you will label it as acidic, basic, or neutral, and it might be incorrect. So it is the weak acid or the weak base, that ion reacts with water. So you could have actually just written the weak ion, I suppose, hey? So the ion that you get from a weak acid or a weak base, what do I mean that you get from? What did we just say? How is a salt formed? A salt is formed by removing the hydrogen. You keep the anion of your acid, but you remove the hydrogen bit and you plug in the cation of your base. So what do you have? Your salt has an acidic and a basic component. And whichever ion you got from a weak acid or a weak base, that's the ion that reacts. All right, so I'm going to show you how I usually do this. And if you have a way, and I always say this weekly, if you have a way that already works for you and you understand completely and you can apply it, please maybe just observe my way, but you really do not have to take on this way as your own. But if you are struggling, hear a different way and maybe try this approach, and it could potentially be your own going forward. All right. So the question, which is from a past paper, it's not in your notes, it's from one of my past papers. By using a hydrolysis reaction, determine whether the salt KF, potassium fluoride, is acidic, basic, or neutral. And now you might go, oh my word, how am I supposed to know this? This is how you go about these questions, because ultimately that is where hydrolysis questions are going to take us, right, in both syllabuses. So whether it's DBE or IEB, this is what hydrolysis does, right? The hydrolysis reaction means that one of my ions have to react or has to react with water. So what do? We break our salt into its ions. Just what does it consist of? K and F. There is one of each, and we know that potassium is in group 1, therefore it is a positive charge, and fluoride will have a negative charge. Right, so our salt consists of potassium ions and fluoride ions. So now I want to challenge you. There's a reason why I wrote the arrow and then the salt, because what did we just go through? We went through proteolytic reactions or acid-base reactions, which form salt and water. For now, I am going to write the plus H2O there, but we're not going to focus on that in this. You don't have to focus on the water at all. You're focusing on your salt, and we are trying to determine which acid and base formed this salt. Why? If I know the acid and the base, I can go, oh, this is a strong acid, or oh, this is a weak base, and I can identify the ion that needs to be written as part of my hydrolysis reaction, or which one could tell me whether my salt is acidic or basic. It's like rock, paper, scissors. If it's a strong acid, like very strong acid, and a weak base, your salt will be more acidic because there's more hydronium ions than hydroxide ions. If it's a strong base and a weak acid, it's going to be a basic salt. Strong overrides weak. So if it's a strong base and a weak acid, strong base, it will be a basic salt. If it's strong and strong, then you've got a neutral salt because they cancel each other out or they work against one another. And then when it gets to a weak acid or weak base, they are weak anyway. So there isn't a high concentration of, so neither will react, but we don't look at weak acids and weak bases. So let's go. Let's try our reverse of what a salt is. A salt is formed when you unplug the hydrogen of your acid and you plug in the metal or the cation of your base. So what is this? This is a cation. So let's write it here. This is going to be my base. So now you're building like a puzzle. You're building your acid and your base. So my base is potassium, we know. So what base has potassium in it? Come on, guys, potassium hydroxide. However, do you know? Because we gave you a table and we said sodium and potassium hydroxide. Group 1 metal with hydroxide, strong base. Remember that. Now, this is the end bit of your acid. How did we form the salt? We removed the hydrogen, plugged in the cation. So now you're going to do the opposite to form your acid again. Remove the cation, and what must an acid have? Hydrogen. So we plug it in, HF. So this is the acid, and this is the base that formed your salt. So let's analyze. What do we know? HF, hydrofluoric acid or hydrogen fluoride, that is a weak acid, WA, weak acid. How do you know? Because you've got 3 strong ones. Hydrochloric, sulfuric, nitric. That one does not fall under those 3. So it is a weak acid. KOH, group 1 metal attached to a hydroxide, is a strong base. Do you see how important it is to know your theory as you progress and not just, it's not a guessing game. It's definitely not how you feel one day, oh, this might be a strong. It really is sit on chair and study. And once you know it, I cannot tell you how amazing the section actually could become. Right. So now we know that we've got a weak acid and a strong base. What did I just say? A strong base will override rock, paper, scissors. A strong base will override the strength of a weak acid. So do we agree that the K bit, the K ion, potassium ion, is a strong ion? Why? Because it comes from a strong substance. So this is a strong ion. And my fluoride ion came from hydrogen fluoride, hydrofluoric acid, which is a weak acid. So this is my weak ion. So which one will react with water? Not the strong, but the weak one. And now this might not make sense because I know only in grade 12 do you actually write the equation out. But just to show you, a hydrolysis reaction is where you need to have, I know that some schools do it in grade 11, so I'm going to show you, and I see your next notes actually looks at it. So I am going to explain, but hang on to it for grade 12. Your weak ion, why? Because the theory states it's an ion that reacts with water, and I told you it's always your weak ion, or the ion that you got from a weak substance. So fluoride ions, they are the weak ones. So it's going to react with water. And this is the only tricky bit actually of this whole process. You want to get rid of an ion. You want that fluoride to become part of a bond. And the only way in which you can do it, you can't donate. This fluoride cannot give anything away because there's only one thing and there's one ion. It can't give anything away. So what's going to happen? It's going to take on an H plus ion. What will it become? HF. And what will happen to your water molecule? It has donated a proton, so it's going to become OH minus. When we started, I told you, hydroxide ions, that's the proof of the presence of a base. Hydronium ions, those are proof of the presence of an acid. So now answer the question. By using a hydrolysis reaction, determine whether KF is acidic, basic, or neutral. What ions did we just form? Basic. So what salt would it be? A basic salt. So this means that it will be a basic salt. So hear me out. This is a long spiel and it is very challenging. I do not sugarcoat. I call a spade a spade. This is one of the most challenging bits of this whole topic or of this whole chapter. But what did we ultimately do? If you're not asked for a reaction, you merely check which substances formed your salt, strong base, weak acid, base overrides acid, basic salt. So you can argue it out by means of using words. But if you are asked for a reaction, the ion that you got, I'm going to highlight those two ions, the ion that was gotten from a weak acid or a weak base, that ion, you must write in a reaction with water. And you always try to get rid of the ion. So if it had a hydrogen in it, it would donate it. If it doesn't, it would like to receive it. So you always try to get rid of that charge. And how could we do it? By water donating a proton. And what you have at the end, that is the type of salt that it would be. So it's a basic salt. Hypothetically speaking, if you had another example and you formed in your equation, hydronium ions were formed, then it would be an acidic salt. And then if you have a strong acid that reacts with a strong base, then you do not use an equation. You merely say that it is a it is a neutral salt, because a strong base and a strong acid, not necessarily they cancel each other out, but they are equal in their reaction with water. So a strong acid and a strong base is neutral. All right. So this concept can sometimes form a little bit of a barrier to our understanding, but just to show you, and this is exactly what we just explained, if you've got a strong acid and a weak base, strong overrides weak, then it is an acidic salt. It's more acidic than it is basic. If you've got a strong acid and a strong base, then it's neutral, even Steven. And if you've got a weak acid and a strong base, then it is an alkali. Why is it an alkali? Because it's now a base that has been dissolved in water. So for those who didn't know the difference between a base and an alkali, a base that has dissolved in water and the ion has reacted, that is what we refer to as an alkali. All right. So just the sentence at the bottom kind of brings it all together. The salt forms an acidic, an alkali, or neutral solution, but that is dependent on the relative strength of the acid and the base. And if you are asked to write an equation, then please remember that the weak ion will react. All right. So that's one of the most tough, I think, bits to do with this section. And you'll see that there's a beautiful explanation here as well as to how you can determine not necessarily the pH, but whether it is acidic or basic or neutral. I do like using a different example than you have in your book so that it's not just study and learn it like a parrot, but you actually know and understand. All right. When we look at indicators, I absolutely love this part of the section, because with indicators, we use color to almost just cement that foundational knowledge that we've now acquired. Everything that we know is now proven by means of colors. And so I do hope that you have seen some demonstrations. I'm not going to show you today, but some demonstrations of acid-base reactions and how we can titrate. If you've done a titration, then great. But how you can use indicators to not just determine whether something is acidic or basic, but at what point have we now neutralized this substance or the reaction. And the term neutralization refers to not a neutral substance. It's not always neutral and on the dot 7. And please note, if anything is 7, it doesn't mean that it is edible or consumable. Water is a consumable neutral substance, but everything that is neutral is not a consumable. So when you refer to indicators, an indicator is a compound that changes color according to the pH of the substance. And so just to challenge ourselves a little bit, pH, potential hydrogen, and so they are very sensitive to a change in a hydrogen atom or ion or a proton that might be added or removed, right? So during titrations, the indicator needs to be selected according to the acidity or alkalinity, then is it an acid or a base, of the salt. So if you know that you have a basic salt, came from a strong base and a weak acid, we always tell you what acid and base you use in a titration. And if you haven't done a titration yet, I find those incredibly fun, and the students usually enjoy them as well. They're quite demanding because you have to be very pedantic with regards to your use, of you turning the tap and making sure that it's not just a constant stream, but drop by drop. But when you use these indicators, please make sure that you use the correct indicator, because certain indicators change color or remain in a specific color for a while, or for a spectrum on the pH scale. So just for you to go through, I know many textbooks and websites have these as well, but phenolphthalein, bromothymol blue, methyl orange, and then litmus paper, which I think, or litmus, which paper form we used quite a lot in prep schools, and then also universal indicator. But when you move into your higher grades, then please note that you use liquid indicators, so it is dropped into, and 5 to 6 to 7 drops is usually more than enough for your prac. So if you look at methyl orange, so if you are told in your prac that you are using acid X and base Y, and then you know that it is a basic salt or acidic salt. Which one would this be? Lower than 7 is acidic. So you use methyl orange when you have an acidic salt. Why? Because the pH is very low, which means it is a strong acid. So your salt must have been formed from the reaction of a strong acid and a weak base to make it a strong acidic salt. So if you ever use a strong acid and a weak base, then methyl orange is the right indicator. Bromothymol blue is what we usually use, because many titrations you'll see that you use HCl and either sodium hydroxide or potassium hydroxide. And we know now that both of those are, whether they are base or acidic, they are both strong. And so your ideal indicator would be bromothymol blue. And then phenolphthalein, I really enjoy this color change a lot more than all of the others. But when in an acid, phenolphthalein is milky white. So it literally looks like milk in your test tube or in your beaker or your flask, whatever method you are using. Some schools really have like micro labs. So sometimes it's like dropping into a small little plastic container even. But phenolphthalein is quite a milky color, and sometimes it becomes colorless in your acid. And as soon as you add your base, then you just see this bright pink appear. And it's very important to do drop by drop, drop and swirl, because you need to get to that point where as the droplet is swirled and the color doesn't go back to its original, but it goes to a pale pink, or with the others, a green or an orange or whatever, that's where you need to stop. That's your equivalence point. All right, so please note the equivalence point is not when the solution is at pH 7, but when the molar amount of the acid and the base is the same according to your ratio, your balanced equation. All right, just keeping my eye on the time as well. All righty, with regards to titrations, or almost finishing off our acids and bases bits, with regards to titrations, there are calculations involved. But with the calculation, there's also a prac setup. So as many schools do it differently, we do a proper burette pipette setup with a clamp and stand and an Erlenmeyer flask and all of those things. But I know that some schools that I actually visited in the week, they did a titration using little like dropper bottles that they got from the pharmacy. And now, because it's smaller scale, you have to be more accurate. So with regards to the setup, I'm going to look at that first, and then we'll do the calculations. With regards to the setup, this is something you need to study. You have to make sure that you understand. If I say study, read through it, understand it, and remember it. Okay, you don't want to be in a prac and then what is a burette? Okay, so please note that the concentration that you know, which is our known concentration, which is our standard solution, right? Your standard solution you usually have at the bottom in your conical flask. Why? Because that is the solution that you just made up. You either diluted it with water, you had to weigh the mass, the correct mass, then dilute it, then do your calculation to get the correct volume. So your standard solution is usually and always actually in your conical flask, because you know that concentration, you know the volume, and now what you're doing is in your burette, you've got your unknown concentration, because you're going to check the volume that you used. Based on that, you're going to calculate. All right, so please note that we must never put our unknown in our flask, because then you can't measure how much you're using. All right, so just having it the right way around is very important. So why are these calculations important? And I know that some schools often teach this formula. And if this is the formula that you use, please, in today's example, continue using that example. But what other schools will do is they will just break it up. So they'll break it up into C is N over V, which is a formula that you're given on your formula sheet. And then what you do is you usually use your known value by that, I mean your standard solution, you'll always have 2 of the 3 variables. And by that, I mean either C or N or V, you'll have 2 of the 3. So you're going to have your standard solution. What do we know about the standard solution? We know the concentration because we had to weigh off what we needed to use. You know your volume, you can read it off your flask or your beaker, whatever you mixed your standard solution in, and then you can calculate your mole. And what is the beauty about the mole? I absolutely love the mole. When you look at the mole, if you've got a balanced equation, you can use ratios. And so from here, and we're going to do one, from here, going from your known value where you had 2 of the 3 variables, you're now going to go to the other calculation, whatever you had in your burette, which we just said is your unknown value. It will make more sense when we do one, please do not stress. So your unknown value, it's still going to be C is N over V. Here, you have now measured the volume. In your burette, you measured the volume that you used until the color changed. And we're asking you to calculate the concentration. So you'll see that you only have 1 variable, but do not fret, because what did you just calculate? You just calculated your mole, and based on your ratio. So how do I get from my known to my unknown? Always use your ratio based on a balanced equation. So then you'll have your mole, and in the end, you can calculate your concentration. All right, so I do know that you've got 2 or 3 examples. You've got 2 examples. So what I'm going to do is I am going to ask us to do an example together, which is not the one that you have in your notes. I always try to put you guys on the spot. Okay, so I hope that it's visible to all. What I did is I already typed out the little steps for you. And like I said, if you at your school use this formula, which is literally what we do separately, just put together, then continue to do so. We know that NaCaVa is usually your first value, so that will be your known, and then NbCbVb will be your unknown, right? But I'm going to do it the way in which I teach it, which is the 2 separate calculations, but you will see the example that you were given. It has titration equations all by first principles. So it's got the long equation, which is actually compressed, and then the 2 separate ones, the one that you've got in your notes. So I would like for us, paper and pen, if you would like to join, that would be great. So I already have the notes here, or the rules, what I would like to maybe suggest that you do and that you follow when you do these calculations, depending on the formula that you use, but it is applicable for both. And then also, when you read a question, and I know in grade 11, we start to think that we're not going to finish our papers, but in your matric year, you could potentially finish with some time to spare if you plan properly, but you could save on some time by just reading properly. So let's do that in this example. It says, in an experiment, 25 cubic centimeters. That should be the first wake-up call, is that's a volume. So I always encourage my students to write V for volume. It seems lame, especially if you think that you've got it, but chemistry has a way of biting you when you are rushed and you do not see certain things. Cubic centimeters cannot be the unit because it is mole per cubic decimeter. So you have to change this to cubic decimeters. And yes, my math is horrible, but I've done this already for us, 0.025 cubic decimeters. In life, always know your flaws. Mine is math. Oh my gosh. All right. So in an experiment, 25 cubic centimeters of sodium hydroxide. There's a reason why I say write down the formula, because you cannot do a mole calculation with a ratio if you don't have a balanced equation. So there we go. So we know that sodium hydroxide, 25 cubic centimeters, which is 0.025 cubic decimeters, is exactly neutralized. It reaches that point where the color doesn't just change, but it actually stays, and it's the color in between. So if you think of bromothymol blue, which is yellow in an acid and blue in a base, the moment you hit a green and you lift it to the lights or on a white tile and you're happy that that is green, you stop. Because that one drop is not just 1 cubic centimeter or 1 cubic decimeter. One drop has a lot of mole in it, quite a couple. So you stop when you reach that green point. Okay, so it is exactly neutralized by 15,1 cubic centimeters, which is 0.0151 cubic decimeters. All right, so that's also a volume of sulfuric acid. So these 2 substances react. So there are your 2 reactants. These 2 substances are reacting. Okay, And then what else do they give us? Of sulfuric acid, we've got that. Of concentration, 0.2 mole per cubic decimeter. So there's a concentration. Immediately, you can also highlight, immediately you need to see that you've got V, volume, and C, concentration of one substance. That is 2 of your 3 variables that you need. So you can immediately start. Your first step, and I'll even just show you, is write a balanced equation. So let's do that first. If we write a balanced equation, we know that we have an acid. So now you'll see I've swapped around the acid and the metal hydroxide so that you don't just learn your rules off by heart, but you can actually apply them. So we remove the hydrogen from my acid and we plug in the cation. So it's going to be Na, valency +1, SO4 2 minus, so Na2, SO4. And our second product is water. So this has to be balanced. And if I look at it quickly, it must be Na2, so there, and then H2H2, 2H2H2, there we go. Right, so that is balanced. 2 there and a 2 there, and we know if nothing is written, then it means that there's a 1. And I'm just plugging those ones in there. So when you do your ratio, you remember to use them as either a denominator, right, in your formula. So there's the first thing, balanced equation. Lovely. So we've done it. Calculate the moles of the known concentration. We know the concentration of the H2SO4. So we're going to calculate the mole of the H2SO4. And we know that N is C times V. And if you are doing this with me and you want to type your answer in the little chat, you're more than welcome to, because you might already be done because I'm taking so long and explaining everything. But we know that N is C times V. And now we know that the concentration we said is 0.2 and the volume, and I'm going to calculate it for us. I brought my calculator. And so we know that the volume we said was 0.0151. Let's keep everything in there. Don't round off in a calculation. Right, so 0.2 times 0.0151, and that gives us 0.00302, and we are in mole. Cool. So that is your second step, done and dusted, and that is the mole value for the sulfuric acid. Some of you do it without steps. You just know what's happening, but that's cool. Then step 2 done. Step 3, use your ratio. All right, so now, and I see that it just says ration. It should be your ratio with the mole value. Sorry, it's not ration, it's ratio with your mole value. And so we just calculated that this okie here, this one is 0.00302. Right, this is my known mole value. We need to calculate the mole value of NaOH. Why? Because we are asked the concentration of sodium hydroxide. We can't calculate the concentration if we only have the volume, but we don't have the mole. So now what the easiest way, in which I think it is the easiest way, is 0.00302, and then you times it by the ratio. What is our ratio? My students have a very interesting way of saying it. Is actually one student, now everyone has taken it as their own way. Where I am going over where I am coming from. You use the coefficient of where you are going as your numerator or unknown over where I am coming from, known. Another way of thinking about it is what I want. We want this mole value over what I have. We have that mole value. So either what I want over what I have, where I am going to over where I'm coming from, or unknown over known, like normal science students would say. All right, so that gives us 0.00604 mole. And now the beauty of chemistry is you now have N, the mole value of sodium hydroxide. You were also given, if you can remember and you look back, we were also given the volume. So we've got N and V. So we now have that mole value, right? We just calculated it. So your last little step is now to calculate the concentration. C is N over V, my mole value, 0.00604. And you divide that by the volume, which we said was 0.025, because you had to convert from cubic centimeters to cubic decimeters. And this one, if memory serves me right from earlier, is 0.2416 mole per cubic decimeter. Right. Please double check the math. And not to be silly, I do know that sometimes I work a little bit fast with the math, but that is the answer. So the answer that you get here is now your concentration of whatever substance you had in your burette, if it's a prac, because your unknown value will go in your burette and your known value will go in your flask. Right, so that is a calculation of a titration. I am going to show you that you have an example. They use exactly the same substances. However, I changed some of the values just so that we don't just copy and paste from our notes. And so you'll see that if you want to, I'm not going to do this example just for time, and we still want to go through some past questions and redox reactions as well. So when you get to this calculation, you'll see that I've taken the equations off, so you can't just look at them. Be very smart and intentional in your preparation. Cover the calculation. Don't just look at it and go, I'll remember it for next time, especially with titrations. All right. We're going to take another break, and then we're going to push all the way to the end. So it is 60. Right. So when we said goodbye to one another, we just finished our acids and bases, our theory. And so we're going to jump right into the basics and the foundation of redox reactions. So just so that you understand a little bit of background, many schools do a little bit of this in grade 10, and then a little bit in 11, and then a little bit in 12, whereas others keep it as a whole section, a whole chunk at the end or close to the end of a grade 12 year. So we are merely focusing on what one should know at this point in your grade 11 year. If your school might have gone a little bit further, then kudos and well done. And if they've done a little bit less, then next time when you are in class and you go through this, then you can answer with confidence. All right, so we're going to start by just looking at what redox reactions are. So the word redox, or the name redox reaction, comes from the two reactions that are involved, reduction and oxidation. And so we will look at what both of these words and reactions mean, or processes mean, but redox, it has to be, or you have to have both of these. One cannot happen individually by itself, independently, and very often one has to happen first in order for the other reaction to take place. So therefore the name redox reaction comes from the reduction and the oxidation reactions that are present in this process. Right, so a redox reaction is a reaction in which there is a transfer of electrons. And so you'll see when you write half reactions, there's always a cation plus electrons, or you'll have your solid on the one side, and then on the other side of the arrow, it loses electrons, but we always use the plus sign, which is very confusing to some students, and we'll get there. But it's the transfer of electrons. Electrons leave a specific side of the reaction or a specific reaction, and it moves towards the other side, or the other reaction, or the other beaker or electrode, depending on what your school has done so far. All right, so oxidation, and I think this is where the studying comes in, and I know you don't want to hear it, but oxidation refers to the substance that has lost electrons. So oxidation, and you'll see today as I go and we say identify, I'll always just write oxy, decrease, oxy loss. Okay, so oxidation is the loss of electrons, and then reduction is the gain of electrons. So if one substance undergoes oxidation and the electrons are lost, they do go somewhere. They're not just lost. We just mean that that substance has given its electrons, right? So please don't just think of electrons are lost, and we always account for everything that is lost must be gained. So I'll show you what the setup looks like in case you haven't looked at that, just to know what a redox reaction actually is. And if your teacher has shown you an actual practical setup, even better, because it's a lot easier to see and understand this concept. But one substance must release or lose its electrons for the opposite subject or the substance rather, an object to take it on. All right, so oxidation is loss, reduction is gain. The oxidizing agent is the substance which accepts electrons. And so with this one, be very careful, because we say oxidizing agent. is not the same as the substance that undergoes oxidation. Oxidation is the process that happens where electrons are released or lost, and reduction is the name of the process that takes place where electrons are gained. When you talk about an oxidizing agent, and this is how I usually explain it, is if I were to be the oxidizing agent, it means that I'm an agent for oxidation, which means I am causing oxidation to take place in the partner beaker or at the other electrode or with the other substance. I am causing oxidation there, hence or therefore I am undergoing reduction. So this is not a definition, it is an explanation. The oxidizing agent undergoes reduction because it causes oxidization or oxidation to happen there. Because oxidation is happening there, I undergo reduction. And what did we say reduction is? The gain of electrons. So the oxidizing agent is the substance that gains electrons or accepts electrons. So it's the one that undergoes reduction. But your definition, please note, is the oxidizing agent is the substance which accepts electrons. The explanation I gave is just to show you that if you are if you are a reducing agent, I am causing reduction to take place on the other side or the other equation. So what am I undergoing? Oxidation, and therefore oxidation is loss. So the reducing agent is the substance that loses or donates its electrons, and it's the one that undergoes oxidation. So if you have another way of remembering it and understanding it, please continue. But very often, even in their matric year, we very often get confused with oxidation and oxidizing agent. So if you are the agent of whatever word you have, oxidizing agent, you cause oxidation, you undergo reduction, and therefore you gain. If you are a reducing agent, you cause reduction, you undergo oxidation, and therefore you lose electrons or you donate electrons. Right, so just to kind of explain what redox reactions are, and I'm not going to ask you to raise your hand or to, just to indicate, but just so that we understand what redox reactions are, other than just reactions that we write on a piece of paper and we need to remember which side our electrons have to go. You will usually have a setup, and I'm not going to go into the detail that is not important for us for today, but you'll have a setup where there's a liquid in one beaker and there's a different liquid. We say liquid, it's called an electrolyte, but that is not important for today. And you've got a different substance in the beaker next door. You have one metal, one type of metal in your one beaker, and you've got a different type of metal. So copper and zinc, cobalt and iron, whatever it might be. You've got two different metals that are submerged in these electrolytes. And so we say that in one of these beakers, one of these reactions will undergo oxidation. And because of that, the other side, the other beaker, the other electrode, or the other reaction will undergo reduction. So just hypothetically speaking, don't worry about what metal we're busy with. Don't worry about the substance that it is in. Let's just focus on explaining by means of picture what oxidation and reduction actually is. Right, so let's say the beaker to your right, the turquoise-ish, bluish color, I'm telling you that is where oxidation takes place, right? Oxidation always takes place at the electrode or at the site, which is called the anode. If this is not how far you've come, please do not start stressing. I'm just merely mentioning because I know some schools have mentioned that. So oxidation always takes place at the part or the site, we always call it the anode. And we know oxidation is loss. So if this is my anode, so this is the side, and I know that it's the loss of electrons, it means that electrons will move in that direction, because this side, your anode, is undergoing oxidation. Oxidation is loss, so surely it must then donate or release its electrons. And this is a conducting wire with a voltmeter. We're not going to worry about any of that. That's for grade 12. But as long as you understand that one site or one side, or we call it one half reaction, undergoes oxidation, the place where that takes place is called the anode. So this is the anode, and the electrons will move. So let's maybe just label a couple of them. And the electrons will move in the other direction. The side that the electrons are approaching, where they are going, we know now that that is where the process of reduction will take place. Oxidation is loss, reduction is gain. So reduction is the gain of electrons, and therefore you'll see that the electrons are moving towards that half cell. And we always talk about the site or the area or the half cell where that takes place. We call it the cathode. So for today, even if you haven't done the picture and you don't know what half cells are and you haven't really actually done any metals reacting, and just remember, oxidation is loss, electrons have to move. And I wanted to draw the picture so that we don't just think of reactions on paper or test tubes with substances poured together. Right, this is a setup, and there's an actual conducting wire, a copper wire, which can conduct electricity. And then we have the voltmeter at the top, because we know the needle moving is proof of voltage. All right, cool. So in looking at those, I hope that the basics of redox reactions will kind of make sense a little bit as we then continue. Right. So you will have these in your notes, and it says oil rig, which is quite a nice way to remember it actually. And so oil rig, OIL, oxidation is loss, and RIG, reduction is gain. And you might ask yourself why I'm going so slowly through the basics of this section, where you'll see as you progress through this section and also going into grade 12, there are many different types of cells that you're going to look at. And if your basics are not solid, then sometimes we have to go back and revise the whole time. So rather revise now. All right. So oxidation is loss, and it's the loss of electrons, and reduction is gain. And it's yet again the gain of electrons. And then you'll see this, I just added this little animation here. Leo-Ger, which is the loss of electrons, is oxidation, exactly the same as oil rig. Says exactly the same. It's not a different rule, exactly the same, but many students just like a different acronym or analogy or example. So LEO, loss of electrons, is oxidation, and GER, as long as you can spell the Leo-Ger properly, because otherwise your acronym's not going to make sense, but this is the gain of electrons, is reduction. And then the last one is what I literally just explained in the diagram, is which process or reaction takes place where. And so if your school hasn't looked at this yet, then now you know what is a cathode or an anode. It is the site, the area, the half cell where this specific reaction takes place. And so therefore we use red cat and anox. So red cat, reduction takes place at the cathode, and anox, at the anode, oxidation takes place, or oxidation takes place at the anode. So this one, and I'm going to highlight it in different color, I just think this is a nice way in your grade 11 year of already making that little jump into your grade 12 of understanding that it's not just two reactions that we write on a piece of paper and electrons are going from one to another. It is an actual physical setup where electrons are moving, and in your grade 12 year, you'll look at what the effect of the moving electrons will be. One of the electrodes will shrink or decrease in size and mass, and the other one will increase. And chemistry definitely isn't magic. So there's always, you can always back it up with either an equation, the periodic table, and rules that you can follow. Right. Then when we get to oxidation numbers, I know for a fact that the IAB, they do not taste oxidation numbers anymore, but I am going to look at them. So when we refer to oxidation numbers and you do follow the IAB syllabus, please don't leave. It's literally going to be a minute or two, but it's nice to understand what the concept means or what the concept is. All right. And so if you've looked at oxidation numbers, you will see that many schools, either there's a table that you're given or you must sit and study them. And then there are also certain, I want to call them cheats or tips that some teachers give. Look at the group which the element is in the periodic table, and that will help you with the valency, and the valency and the oxidation number can very often be the same. So what I'm going to do is how you remember it and how you are taught. We have many different ways, but I'm going to go through just the rules for assigning the oxidation numbers. I'm literally going to go through these 9 very swiftly, and then we'll do a little exercise where we're going to practice. And yeah, if you are IAB, it's just nice to actually know and understand. All right, so pure elements and diatomic elements are usually 0. So if you look at O2, even though there are 2 oxygen atoms, and what is our little acronym? And now I can see if you've listened, and I hope some of you are saying it out loud in your room or in your study, wherever you are. Have no fear of ice cold beverages. And then you just plug a 2 in there. What are these called again? They're called not polyatomic ions, but diatomic molecules. Di meaning 2 of the same atom forming a molecule. All right, revision. So pure elements and diatomic elements, they are usually 0. And so some of you know these rules. I'm just going to glance over them very swiftly. Hydrogen is +1, except when bonded to a metal, then it is -1. But then also, if you think about where hydrogen is situated on the periodic table, which we have checked out today a little bit earlier when we started, hydrogen is in group 1. So it's always +1, except if it is bonded to a metal, then the plus is just a negative, but it's 1. So if you just want to know the numbers and then the signs, you can study the rules. That could also help. Right. Oxygen, usually -2. So yet again, oxygen is in group 6 on the periodic table, and there are 8 groups. So if you want to know the number, except if there are exceptions like the ones in brackets, which I'll just go through. But if you do have your little periodic table, then you know group 8 minus 6 is 2. So the valency of oxygen is 2 minus, and therefore unless it is attached to or bounded to or bond to, if it is present in a peroxide. All right. So these are rules that you really have to sit and study. I'm just going to look at them very swiftly. Metals equal to the group number. Right, so if it's group 1, sodium, lithium, sodium, potassium, rubidium, cesium, francium, there you go, group 1. Group 2, your magnesiums, your potassium, no, not potassiums, magnesium, calciums, there you go. I almost forgot. And then group 3, and please note that you also have transition metals, and therefore the Roman numeral is very important. You have copper, and copper could be +2, +3. The same for something like iron, cobalt. Many of them are quite versatile in nature. All right, the oxidation number of a monoatomic ion is the same as its charge. So zinc, zinc 2+. Right, that's also the number or amount of electrons that it will gain or then that it will lose depending on oxidation or reduction. I'm going to kick up a notch just so that we can do some questions. Group 17 elements, always -1. If you think about it, you've got group 1, group 2, transition metals, group 3, and then from the other side, your noble gases or your inert gases, 0, -1, -2, -3. So that's an easy way to kind of remember it, right? So just make sure that you have a way in which you could potentially check. Right, then the oxidation number of transition metals, we said stock notation, or then Roman numerals. All right, please note that you understand how Roman numerals work. I know this sounds highly silly, but your Roman numerals, if you've got the straight line, those are single digits. If you've got a V, it's a 5. If it is before, then it is 5 minus, and if it is after, then it is 5 plus. I realize that some students were uncomfortable with that. Then in a neutral compound, the sum of the oxidation numbers must be 0. So if you have a compound that is neutral, if you've got a +2 and you've got a -1, then you must have 2, like a subscript 2 of the -1. Your charges, I always say to my students, whenever you look at a compound, the charges can be equal, opposite in sign. That's perfect. But you must have them balance out to have a neutral compound. And then the last little bit is, in a polyatomic ion, the sum of the oxidation numbers is equal to the charge of the ion. So the sum is equal to the charge. And so you will see with representing redox reactions, which I'm going to look at first, and then we will practice the oxidation numbers. You'll see the oxidation numbers is something that you literally have to apply, study the rules and apply. Whereas when you look at representing redox reactions, I want to show you a nice little way in which you can check whether your reaction is actually making sense. Okay, so redox reactions can be shown in 2 half reactions, which means one of your reactions must have the +2 or 1 electron on the left-hand side of the arrow as a reactant, and the other reaction must have it on the other side of your arrow. We'll look at oxidation and reduction now, but that clearly indicates that one substance is losing, undergoing oxidation, being the reducing agent, and the other substance is undergoing reduction, gaining the electron, which then means that they are acting as the oxidizing agent. So when we look at these half reactions, your oxidation half reaction, the electrons are shown as products, right? When it is the oxidation, because you started with a substance, and then what happened? If it is oxidation, we know oxidation loses. So you start with a substance on your reactant side. Arrow means transitioning from your reactants to your product. So this substance has lost, it has given away. So therefore your electrons will be on the right-hand side as part of your products. If you have another way of remembering it, I know that some schools immediately, your teachers have shown you the standard electrode potential table. So if you know what I'm talking about, then maybe just pay a bit of attention. And if you don't know, stress. We all go at different paces and schools do things differently. So some of you will understand and remember oxidation, my electrons on the product side, reductions, electrons on my reactant side, and that's perfect. But if you have been exposed and introduced to the SEP table, which is that big table with all of the half reactions, then you will also know that you must write your oxidation from right to left and your reduction from left to right. If you've done the SEP table, you will know what I'm talking about. If you haven't, this is the rule that you must follow, or this is the way in which I would remember it if I were you. All right, your reduction half reaction, we show the electrons as reactants. So you'll see that they are to the left of our arrow, which means a substance that I have, it is gaining electrons and therefore it becomes. So that's my way of remembering. With oxidation, I have a substance and then it releases electrons. Electrons are written as products to the right-hand side of your arrow. Whereas with reduction, you've got a substance that gains electrons and then becomes. So your arrow, note that your electrons are to the left. Right, and then you can also do a net reaction, which we have looked at what a net reaction is earlier today in our acid and bases section. So with a net reaction, it means that your electrons are not shown. Why can we just throw them away? If you think about combining these two half reactions, you've got one reaction. I don't want to say see it as an equal sign, but in math, if you've got one value to the right-hand side of your arrow, and you take it across, and you've got the same value already there, and the sign changes. If you've got 2 to the left-hand side of your arrow, and you've got 2 to the right of your equal sign, you take the 2 across, it's going to become 2 minus 2, so they cancel each other out indirectly. So what you can do is, when you get to a net reaction, you take your oxidation and your reduction half reactions, and you merely cross out your electrons, if they are of the same value. If they are not, you have to coefficient multiply to make sure that they are, but you cross them out. And whatever you are left with, you now combine into a reaction that shows me all of my reactants, except for electrons, and all of my products, except for electrons. So let's check if this is what we have. Here we've got X as a reactant, and here we've got Y as a reactant. X plus Y, sorted. Electrons are equal in number, so they cancel each other out. What do I have? And I'm going to include a little step here. What do I have as a product in my first reaction? We know that we've got X2 plus. And what do we have as a product in my second reaction? We have got Y2 minus. And so where did they get this from? You're writing a formula, you're forming something new. And so the valencies are equal but opposite in charge, and therefore you need one X, one Y, and therefore the 1 is not written as a subscript. So I just wanted to explain that because I saw this and I thought, this might be slightly confusing, the net reaction. Right. I want us just to practice to write a net equation or a net reaction. And so what we're going to do is, I have just given you these 2 half reactions. I'm not asking you to identify which one is oxidation and reduction. I've given this to you. And so oxidation, we know, is loss. And so therefore the electrons are written to the right-hand side as products. And then we just said that reduction is gain. And therefore your electrons are written to the left-hand side of your arrow. I do know that many students, they write it in such a manner that the arrows are exactly underneath one another. That's actually quite smart. And therefore you can see what are reactants and which ones are products. If that's you, perfect. Please continue. Right. So what we're going to do is the following. We want a net reaction, which means a combination of both reactions without electrons. In the previous example, it was quite easy. We just said, oh, 2 electrons to the right, 2 electrons to the left, cross it out. But in this equation, it's not really the case. Or in this example, you have 1 electron and 2 electrons. And so here's a little trick, you might know it. You literally just multiply by adding a coefficient to everything in your equation to make sure that your electrons are equal. Why can we just add a coefficient? Because that's a ratio. And 1 to 1 to 1 is exactly the same as 2 to 2 to 2, 4 to 4 to 4. So all you're doing is you're ensuring that if I were to cross out my electrons, that I've multiplied with a coefficient to make sure that your equation will be balanced in the end. Whatever you have as reactants, you need as products. They have to be accounted for. So let's check. I'm going to highlight all of our reactants, one specific color. That is to the left of an arrow. Reactant, that's to the left of an arrow. A reactant, product, and product. So here we go, our net reaction. And please note, if you wrote 2Ag plus first, it's fine as long as they are on the correct side of the arrow. You can't swap reactants and products, but you can, however, swap 2 reactants around their order, I want to say, and your product. All right, so we've got Mn, and we've got 2Ag plus, which is 2 silver ions. And then, ooh, I made a mistake here. That should be Mn2 plus. There we go. See, this day has been very long. And Mn2 plus, and we crossed out our electrons, and our second product is then 2Ag. Some of you might have picked up on this error. I apologize profusely. So what is our net reaction? All of our reactants from both reactions combined with, and then arrow, your products from both of your reactions. All right. So those will be examples of representing redox reactions. Cool. If we look at oxidizing and reducing agents and then the oxidizing numbers, I am going to look at this example. I do realize that this is one that you have in your notes, but just to show you that the oxidizing numbers, for those who do oxidizing numbers, are actually quite easy. And then so this will be for DBE. And then for IEB students, I'm just going to look at how you can identify which one has undergone oxidation and reduction without having the half reactions, which actually comes down to exactly the same concept as oxidation numbers. All right, so let's finish strong, guys. You have done well. We've got 50 minutes left. Let's go. All right, so in the following equations, identify the oxidizing and reducing agent. The agent has undergone a process. Remember which one is which. Step 1, write all the oxidation numbers. So copper, you can't just know, oh, copper is 2, because copper could be something else because it's a transition metal. But what do we know? Oxygen is -2. It's in group 6 or 16 then. So it's -2. And a compound that is neutral, the charges must balance out. So therefore, copper must be 2 plus or +2. Please note, if you write +2 or 2 plus, that is irrelevant as long as it's the right thing. What is this? We know that this is a diatomic molecule. So immediately you must remember, and therefore we know that the valency, sure, that the oxidation number is 0. Right. Then if you look at copper here, it's by itself. So it does not have a charge, if you must. So it is 0. Now here is a rule. Hydrogen by itself would be 0, except if, okay, so please remember. So it is +1 and -2. And now you might go, oh, they are different. Yes, they are. But what do you see? Your hydrogen has a little subscript 2, which means, yes, it's +1, but there's 2 of them, which technically makes it +2, and therefore it can be formed with or attached to a -2. All right, step 2, identify the change in oxidation number for each element. So your copper, let's take it one at a time. Copper went from a +2 to a 0. So it was positive by 2 and then became neutral. Remember that. We're going to revisit that in a couple. Then our oxygen, if you look at O, it went from a -2, stayed -2. Right? Great. And then lastly, hydrogen went from a 0 to a +1. So now you can ask yourself, I know the answers are written here or typed here, but as you identify which one has undergone oxidation, oxidation is loss, reduction is gain. So automatically they just say that copper, right? It went from Cu2+ and it became Cu without a charge. I'm just going to pop a 0 in there. Without the charge, without the oxidation number, it's now neutral, right? So if you are positive, right, to become neutral, what reaction or process must you undergo? If you are positive to become neutral, you can't lose positivity. You can only lose or gain electrons, right? Acids and bases, the donation of a proton, separate section. So as this substance is now undergoing a change, it's either losing electrons, oxidation, or gaining electrons, reduction. So here we go, Cu2+ to 0, it has gained electrons. Why would I say that? If you're positive, you gain 2 electrons, 2 negative charges in order to become neutral. They balance each other out. And then if you look at hydrogen, because oxygen, there was no change. So hydrogen was neutral, 0 charge, and now became positive. Can't gain positivity in life, you can. Chemistry, not as much. So it was neutral, charge of 0. It had to lose electrons or an electron. So hydrogen went from a 0 charge to an H1+, and therefore it has lost. And so the question was, which one is the oxidizing agent and which one is the reducing agent? So if it undergoes oxidation, oxidation is loss. If it undergoes oxidation, it is the reducing agent. So I know that it is there in front of you, but I'm showing you how to get there and argue it out with yourself. Don't just do the answers and, oh, I'll remember that for next time. Right. And then gaining is reduction. And we know that that will then be the oxidizing agent. All right. So I think this is quite a nice example. I'm not going to do all of them, but it's quite a nice example of how to look at oxidation numbers. Right. For IEB students, I'm just going to look at, and actually for DBE as well. So it's not just IEB, DBE, we do exactly the same work with a couple of changes. But if you were to look at this example that we have here, so Mn is manganese, by the way, and I see some of you going, well, what is Mn? So manganese and silver, they are part of a setup, and there are 2 half reactions. And now if you don't do oxidation numbers, do not stress or fret, because now we're going to show you. You look at the charges that they have. So as a reactant at the start, Mn was neutral. What did Mn become? 2+. So Mn, so very similar, was neutral, became Mn2+, which means that it would have lost. So imagine that you don't have the half reactions at the top. Okay, so I know we've done this one, so it's a little bit sad and lame, but imagine that you don't have the oxidation and the reduction half reaction. I'm giving you a net equation and I'm just saying, identify which substance is the oxidizing agent and the reducing agent. So exactly the same question, just a different approach. Right, so manganese went from Mn 0 to 2+. So it has lost electrons. Oxidation is lost, so we know that this will be the reducing agent. Right, I know I'm taking time to explain this, but I cannot understand why we make it difficult for ourselves, but I don't know. You can see it, figure it out. Let's go. Okay, silver is +1, and then it is a neutral. So we know obviously that it will be the opposite, but if you started with that one, for instance, we know that silver to Ag+, then became to Ag neutral, which means from positive to neutral, you can't gain a positive charge or positivity in chemistry at least. So they gained, right? So gained electrons, we know that that is reduction, and therefore that will be the oxidizing, and I'm going to write it out for those who are doing this with me. This will be the oxidizing agents. All right. So very easy way. I don't think that oxidation numbers are very difficult. I do think, however, that if you do not know those rules, that list of 9, I think, I am going to just remind myself of 9 rules. If you do not know those rules for the DBE students, you might be in a bit of a pickle, but if you are an IEB, you don't have to know those rules. So there's one thing that we have slightly different to the DBE. All right. I just want to refer to these examples. I don't want to like skip them completely, but there is ample time for some questions, which is great. But use these examples in your own pace or at your own pace to look at and to make sure that we are comfortable with the following things. So this is us taking the section together, because that's literally redox reaction so far. All right. As you go through these examples, and you'll see that we're going to get to 2 to 3 of the questions that you were sent as well, the past papers. We definitely won't be able to fit all of them in. But as you do these redox revision notes, and as you start prepping when your exams do come, please make sure that you're comfortable with the following. Know the difference between oxidizing and reducing agent. So we are recapping. An oxidizing agent causes oxidation, but undergoes reduction, and reduction is gain. So an oxidizing agent gains electrons. A reducing agent causes reduction, undergoes oxidation, and therefore loses electrons. So just don't think that oxidation is the oxidizing agent, other way around. Okay. So when you're comfortable with that, please note that we also kind of expect you to be comfortable with the fact that oxidation, let me write it here, that oxidation takes place at what we call the anode. So anox, and that reduction, I'm just going to write red, that reduction takes place at what we call the cathode, red cat and anox. And if you are DBE, make sure that you're comfortable with those 9 rules as to how to identify your oxidation numbers. And then if you are IEB, it's nice to know those rules. It could make life a little bit easier for us as well. But for IEB, you can merely do the example that we just did, where you look at what it was as a reactant, what it is as a product. As much as we don't refer to oxidation numbers, we're looking at the charge that it could potentially have. And if it was neutral, so for both DBE and IEB, if your substance that you started off with was positive and then became neutral, it gained electrons. So oxidizing agent reduction took place. And if it was negative or neutral and it became positive, then it has lost its electrons, which is oxidation, and therefore the reducing agent. Almost slip of the tongue and said it wrong way around there. All right. We are going to just want to see, oh, this is just another example. We can actually look at this one if you want in your own time. Just before we do exam questions, I forgot that I added this one. You'll see that magnesium is by itself, and here it is part of. And then we'll see, I'm going to highlight all of them. Then you'll see that iron is part of, and then it is by itself. And then the last one, you'll see that sulfate is part of and part of. So if I mean part of, I mean part of a compound. It's not by itself, because what do we know? If it's by itself, you can refer to this as being a 0. Sulfate is a 2-, so magnesium should be 2+. So I'm just going through this by means of oxidation numbers or not oxidation numbers, and just checking what it was and what it is now. Whichever method you are expected to use, this is how you can go about it. So sulfate, 2-, so Fe will be 2+, and here Fe is by itself, so it is neutral. So now what do we see? Immediately we can eliminate sulfate because it stays the same. In one of the examples that we've done as well, I think oxygen was the one that stayed the same throughout. So you just immediately ignore it. That cannot be oxidation or reduction. So I'm asking you to identify exactly the same as what we've been doing. Which one is your oxidizing agent and which one is the reducing agent? So magnesium went from a 0, and then it was a 2+. This is just me writing. This is not a specific format. Please note, I'm just making notes as we go. And then iron was a 2+, and then it was a neutral. So just for yourself, neutral became positive, lost electron. Some of you will immediately go oxidation, reducing agent. Beautiful. But I'm going for all of us. level playing field. So it was neutral, became positive, so it lost electrons. We know that that is oxidation, and that will make magnesium the reducing agent, right? And then iron went from a 2+ to a neutral, which means that it had to gain electrons. Gained electrons, that is reduction, and that is what we call the oxidizing agent. Right. So with that in mind, please note that it looks more daunting, I think, than it actually is. Right. And I'm going to prove that to you. We're going to do some questions together. So I know that you've got this document as well. And what I did in our break is I looked for questions that we can go through that kind of looks at the most theory. So I'm going to go through questions that look at the most theory so that we can not cram, but summarize what we've done today. All right. So I'm going to start. If there's time to do more, then we'll definitely do more. I'm going to start by looking at question 1.2. So this one here, and how I usually do it is we look at the question and then I just scroll to the side and I do the answers there. All right, so question 1.2. So we're now back to acids and bases first. All right, we are going to push through without a last break. Just checking the time. Yes, I hope you are okay. It's going to be worth it, I promise. All right, so question 1.2 based on acids and bases. And then if there's more time, we can come back to do more. Right, A, explain why. So firstly, sorry, let's see what they give us. Ammonia can readily dissolve in water according to the equation below. So this is where you're going to get a little bit tired of my revision, but it does work. Before we look at the questions, I almost just jumped into a question. Before you look at the question, let's revise by looking at this equation, what we know. This is ammonia. I'm not going to make notes of everything, otherwise I won't have space to write. But ammonia is a covalent bond. Therefore, it has the reaction with water plus H2O. No water on the arrow. Okay. They just say that ammonia can readily dissolve. What type of substance is ammonia? I think we know now that it is a base. So it seems silly, but make these type of notes, maybe not in your exam, but as you prep, most definitely. All right. What do we know before you even look at your products that they give you? A base is a proton receiver. So I would immediately just do that. Double check that your products are correct. NH4 plus, great. OH minus, great. Hydroxide is the proof of the presence of a base, lovely, and you know that your AQ is the phase. Okay, so you take a couple of moments just to familiarize yourself with your question. Let's go. A, explain why a hydroxide ion is regarded as a Lowry-Bronsted base. And so this is a little bit of, I want to say, theory that we actually just had to study. It's not really a very difficult question. They're not always trying to catch you, but why is a hydroxide ion a Lowry-Bronsted base? Because it is a proton acceptor. So I will write it in here. I'm not going to do the whole definition, but we know that a base is a proton acceptor. And so acceptor is the word that we use in the CAPS document and in the SAGS document. And so I always kind of encourage my students to use the word acceptor and not receiver. But anyway, I suppose it could potentially mean exactly the same thing. All right, but it is a proton acceptor, or it acts as a proton acceptor. All right. Question A, done. B, identify the type of bond responsible for the formation of the ammonium ion in the above equation. So in our above equation, I'm not going to keep on zooming in. I'll just keep it as it is. In our equation, that is our ammonium ion, but they're asking us what is responsible, what type of bond is responsible. And now you've made the notes, so you don't have to go and what type of bond is it? But even if you didn't make the notes, nitrogen, hydrogen, two nonmetals, covalent bond. So what type of bond is responsible? B, that would be covalent bond. Okay, So I go through these questions very often, and I think we overthink it. We make it way too difficult, way more difficult than it should be. All right, C. Write a balanced equation to show how the amphiolites, and now some of you are going back through your notes, what is an amphiolite? Okay, to show how the amphiolite in the above equation will act as a base when it reacts with hydrochloric acid. And so what is an amphiolite again? A substance that can act as an acid or a base. And in this example, I'm just going to refer to the most obvious one that we have dealt with, and that is water. And so what they're asking us is to write a balanced equation to show how the amphiolite, water, in the above equation will act as a base when it reacts with hydrochloric acid. So I am going to write it here to the side. So the fact that they say the amphiolite reacts with hydrochloric acid, guys, that doesn't mean that you have to write water plus hydrochloric acid. HCl plus H2O means exactly the same thing. So you must just write in a manner that makes it understandable and easy for you. All right. So they're asking us to follow and complete this equation. So how can we complete it? They tell us that it reacts with an acid. And so the acid has to donate. So be very careful. We can say, how would water react as an amphiolite in the reaction with? And then we'll say sulfuric acid. Then you can't stress and go, but I don't know if it must react as an acid or a base. It is reacting with an acid. So surely then the water must act as the base. So it's all relative. And this is what I said in the explanation as well. It's all relative and very dependent on that specific example. All right. So with this example, you'll see that I'm now just turning it up a little with just swapping the two reactants around. Some of us already, we do not know what's happening. So HCl is donating your hydrogen or your proton, your hydrogen ion. So you will be left with Cl minus in aqueous solution. I will practice what I preach, and therefore you will be left with, or not be left with, but it will form H3O plus, and that is also aqueous solution. So what have we just done? You've written a balanced equation. Make sure that it is balanced. You've written a balanced equation to show how the amphiolitic substance can now potentially act as a base. In the previous one, it was acting as the acid, and now it is acting as the base. So let's just double check H2O, and there's another H3O, Cl. Done. Beautiful. All right. So that was question C. Lovely. I did some of these in our break just to make sure that they actually include all of the theory that we need to look at. So let's do this. Right. Let's look at what they give us, and I'm going to analyze as I go. And I do apologize if this is maybe not the way you do it. Please continue the way in which you do it. And here, remember that you have got 2 or 3 different options for calculating. Right, so this is a titration calculation. And for now, for your grade 11 year, that is one of the only calculations, mathematical calculations that you will need to do in this section. So let's go. 5 cubic decimeters of nitric acid. I'm going to highlight everything acid related one color and everything base related another, so we can see which one is our known solution or concentration, because I don't always tell you. So let's see. With a concentration of, barely finished that sentence. So we've got nitric acid. We also have, if you want to do it the long way that I do, that is a volume, that is a concentration. So if you're doing it the way where you do the 2 separate calculations, surely it must be clear that you're going to start with with nitric acid. We haven't even read the rest of the question, but I already have 2 of my 3 variables, and there are only 3 in the formula, so you can see where this is going. Right. Then it is spilled accidentally in a small pond of water. The acid and water has a total volume of 1,000 cubic decimeters, right? To neutralize the acid, calcium hydroxide is added to the water. So calcium hydroxide, right? So I have to be honest, a lot of words and a lot of things that they tell us, that is a volume, by the way, but it really isn't that challenging because you have exactly what you need to get started. So I have done both ways. However, I am just going to do the way that I teach, and you'll see in the memo, we've done the DBE and the IEB way. So just for time's sake, I'm going to do the way in which I teach, and just so for the IEB students, and then another one, if we get there, I'll do the DBE way, and then we can see both. But our answer should be exactly the same. So first things first, we have got, let me just see, it was for nitric acid 5 and 0.05. You don't have to convert to this because it is in cubic decimeters. They are so kind. Right, so we know when you look at C is N over V. Many of you will now just plug in the values, and I'm going to do it that way, and you will have 0.75, and you won't have the mole value, but you'll have the volume, which is 5. And then you know that the 5 will just go across, and that's beautiful. But what I do want to encourage you to do, and so I'm going to take this off, I want to encourage you, before you even start with a calculation, try and manipulate the formula without plugging it in. You won't lose marks for what you just did. It's beautiful, it's perfect, but try to understand what it is that they are asking and what you're trying to calculate, and manipulate the formula so that that unknown variable is the only thing you've got to the left-hand side of your arrow. All right, or of your equal sign, excuse me. So we've got concentration and we've got volume. And so we know if you manipulate the formula, I'm going to show you how to, just for those who might not be very comfortable with math. Some of us never know, is it now going to be divided by or multiplied by? If you want to get rid in math, if you want to get rid of a denominator, what do? You multiply by that denominator over 1. Okay, so they cancel each other out. What you do to the right, you must do to the left. Or what you do to the left, you must do to the right. You can't just add something. It has to be accounted for. So the same with balanced equations, right? So what do we know? If you do that, you're going to multiply by V over 1, which is exactly the same as V. So in the end, what will you have left? You will have, I'm going to write it the way it is, CV equals N, and I always just like my unknown to be the only thing to the left, so I'm merely just going to swap them around. So you're going to have N equals C times V. If what I just did confused you completely, please, that is just a skill that I think by the time you get to your final exam in matric, especially if you think about physics as well, it's really important to be able to move variables around to get your unknown by itself to the left. It really does eliminate some mathematical disasters later in life. Right, so concentration we said, and volume we have. So we've got 0.75. Sorry, I did it earlier so that we don't have to spend time with me calculating on my calculator. And that will give you in the end, so this is the mole of the nitric acid. Right, and that will give us 3.75 mole. Right. But now I did not do the first step. If you can remember our titration steps, I didn't really write a balanced equation. If you were to look at the this equation, which they gave us, which is quite great, okay, so you've got the mole value, you've just calculated this mole value, all right? And now you know that calcium hydroxide was added, and so calcium hydroxide, that OK was added. So you now have to use your mole value and then use your ratio to get the mole for calcium hydroxide. Okay, so that's, I'm going to call this step 1. Step 2, we've just calculated this mole value, 3.75, and we now have to multiply it by a ratio. Our ratio, we have the mole value for nitric acid, we're going to calcium hydroxide. So where I am going over where I'm coming from, what I want over what I have, or unknown over known. And therefore you will multiply that by 1/2. And I see that in my calculations, I actually didn't do this step. So I am quickly going to do that. Some of you are doing it literally just off the top of your head. That will give you 1.875 mole. And we know that this is the mole for the calcium hydroxide. Okay. So this is the mole for the calcium hydroxide. Right, then step 3, the last step, we know that C is N over V. We just calculated the mole, 1.875, and you've got the volume. They say that the volume is 1,000. And so I am literally just going to do this. It's divided by 1,000, so it is 1, 2, 3. So your answer is going to be 0,001875. Well done, Akira. You are way too fast for me. You could also write it in scientific notation, which is something that I'm definitely not going to revise today, especially with our limited time and more questions that I would like to do. You could also potentially just go 1,875 times 10 to the 1, 2, 3 to the negative 3. Please remember to have a unit. It is mole per cubic decimeter, right? Because it's concentration. And so your concentration of the sodium hydroxide, that is what you just calculated. Right. I do see that that was question E. I apologize. I just wanted to do the calculation immediately. But they do ask you, D, define the term concentration. And here is the definition. I'm going to read it. I'm definitely not going to write it. It is in your CAPS and in your SAGS document. So concentration is the amount of solute per liter of solution, or the concentration is the number of moles of substance in a specific volume or per unit volume. So please note, DBE and IEB definitions are not always the same. I repeat, they are not always the same. They're not always different, but they're not always the same. So please make sure that you are comfortable with your own syllabus definitions. All right. If I am going to skip, not because I don't want to do the calculation, but if you look at the question, it says, use calculations to determine if 120 grams of calcium hydroxide will be sufficient to react completely with all the acid in the pond. So that is a limiting reagent, excess reagents, and what you have and what you need to form that. So I'm going to just, for time, because we are talking about redox reactions and acids and bases, and so that's a stoichiometrical calculation, which I think one can do with some effort. All right. So what I am going to do is I am going to just jump to one redox reaction question. And then if we're not done, or if we are done and there's time, then I'm going to revisit some individual questions, and we can then open it up to questions for you guys as well after this very long session. All right, guys, you're doing incredibly well. I hope you're still with me. Cool. Let's look at question 2.2. Please note that this is now referring to our redox reactions. So yeah, no more acids and bases for now, unless there is time. So let's see, they say, when HCl is added to a zinc solid, it produces zinc chloride and hydrogen gas. And then a note of advice and maybe a note of warning is it just doesn't say anything about a balanced equation. It just says when HCl is added to zinc, it forms zinc chloride and hydrogen gas. If this reaction was not given, I actually should have erased it so that we can write it together, which was actually a great exercise. But if you were to get the word equation, but not the reaction, please focus on the following. When your zinc chloride is formed, that you remember your subscript 2. It happens very often where we're rushed in an exam, it's just ZnCl. But zinc has a valency of 2. Well, chlorine has a valency of -1, and there's 2. And so you need to make sure that you just form the correct formula or write the correct formula. And here, it's a polyatomic ion, diatomic molecule, hydrogen gas. Right. So I know they give this to you, but please just be wary. And now they don't say that this is balanced. And so I know that there are questions that will follow, so I don't want to get ahead of myself, but they give you this equation, and we can see that there's 1 hydrogen, 1 chlorine, 1 zinc, 2 chlorine, 2 hydrogen. So clearly there could potentially be a question on balancing the equation as well. All right, but please note balancing changes nothing with regards to oxidation or reduction. All right. So just things that I wanted to point out. Alrighty, give the oxidation numbers for ZnCl and for H2. So what I'm going to do is I'm just going to write it up top here. So if you think about it, they say the oxidation numbers for ZnCl, which means you're not going to take everything in this whole equation. You're literally just going to take the ones that they have asked you. So for zinc chloride, let's check. Chlorine, we know, is -1, or chloride ions, -1. your rules, if you're doing oxidation rules, if you're just looking at what they were in a bond and what they are after, and then this is exactly the same way. So chloride ions, -1, and you see that there are 2 of them. So the total of your chloride ions or chlorine then will be -2. And therefore we know that zinc is 2+. All right, because zinc is a transition metal. So you can't always go, it's always going to be 2. It is all relative to what it is attached to, or with rather. Then hydrogen. Hydrogen by itself, we've spoken about the gases and we've spoken about our diatomic molecules. And so you should know that it is 0. So in answering a question like this, I just wanted to show you, if you answer a question like this, then maybe in this space, maybe just write Zn, and then it is a 2+. And then Cl, and then you write it is a 1-. Just so you don't just do it on, I know that you've got to write on papers, your final matric paper is now a write on for chemistry, but there's always a space. So just write clearly. Okay, and then hydrogen, we know it is 0. And then many questions come up, not in this session though, but many questions come up often about the oxidation numbers and about the equation, but it will change when it's balanced. It won't change when it is balanced. That's the beauty of it. It is allocated to each element. The oxidation number is for the element. And so please note that that is why you can just go ahead and do that. All right, so we've done A. You'll see that I'm not rushing through these questions because there's plenty of time for you to also go and work individually and independently, but it is important to focus on many things together as a group. All right, define a redox reaction. So here's your definition. A redox reaction is an electron transferring reaction. So they're not asking you what an oxidation or a reduction reaction is. They are merely asking, define a redox reaction. So it is a reaction where there is an electron transfer, or it is a electron transferring reaction. All right. Be done. Consider the following half reaction. And so there is our half reaction. And by just looking at it, don't even look at the questions. I'm going to just take them out of the shots. And this is where many of the matrics that I've seen for sessions the past couple of days, they say it's actually a nice approach. It takes time, but it's a nice approach. Don't look at your options or don't look at your questions. Multiple choice. Read the question, cover your options, and choose the correct answer that you know should be the answer. And then look at the correct one that is closest to yours or identical to yours. So the same with these longer questions. What do we know? If you look at 2H, you see that it was a plus, and then it became a neutral. And we can see that it gained electrons. Right? So what type of reaction could this maybe be? You've got a 50-50 chance of getting it right. So I always say to my students, put yourself out there. But ma'am, I don't want to get it wrong, but you could potentially get it right. So what do we know? If it's oxidation, then it loses. Oxidation is lost. And then you write your electrons on the right-hand side of your arrow. If it is reduction, it is gain. You write it on your left-hand side. So even if that wasn't a dead giveaway, you could have seen it was positive. It became neutral. Ooh, this must be a reduction reaction. So now I'm taking millions of minutes to just write a couple of notes, but explain your work to yourself while you're doing past papers or worksheets or questions or whatever it is that your teacher supplies you with. Okay, so reduction, and this was a gain. All right, so who knows, they might ask that. Cool, let's see. Consider the following half reaction. There it is. What is this process called? Reduction. There we go. So this is reduction. And now they're asking, so please note, I always say to my students, just note the numbering of the questions, all right? If you have a 5.1 and there's a 5.1.1, 5.1.2, then all of those are still part of 5.1. So the same here. We've got question 2.2, and so we're doing exam 101 here. But if you've got question 2.2, and then you see there's A, B, more information, C, D, C follows on B and A. So they're all compressed together as part of the big holistic question. So don't just see this as now a separate question. We're still busy with the hydrochloric acid, zinc, forming zinc chloride and hydrogen gas. All right, so let's see. The question, use the above so the above, meaning this, as a template and write down the other half reaction. So we know that this is the reduction half reaction. So the oxidation half reaction must then start with, so we see that we've got two options. We've now already used H, I'm going to cross it out. We've already used hydrogen in our reduction half reaction. So look how sneaky they are. Now you've got two options. You've got Cl and Zn, chlorine or chloride ions, and zinc. Why can it not be chlorine or chloride ions? Why is that not the one that undergoes oxidation? What do you see? It is part of, remember earlier I said part of, it's attached to, it's part of a bond, right? It's part of a bigger molecule or a bigger substance. And here on the product side, it's also part of, I should maybe just encircle chlorine by itself. It's also part of, so it can't be Cl, because that's a question that pops up very often is, ma'am, why can't it be Cl? Because Cl has an oxidation number and it has an oxidation number, like it stays kind of the same. It doesn't change. However, zinc, what do we see? Zinc went from a neutral, and I'm just going to take this off quickly and then I'll go back to the question. So it's in shot. Chlorine or chloride ions, -1, but there's two of them. So it's actually -2. So what must zinc then be to balance it out? Zinc 2+. So zinc went from neutral to zinc 2+. And what do we know? When it is oxidation, where do you write your electrons? Reduction, you write your electrons to the left. Oxidation, you write it to the right. So let's use the above as a template and write the other half reaction. So we have got zinc, which is by itself, +2 electrons. Is that correct? No, you have to write it to the right. Just checking whether you guys are awake still. I don't think anyone responded, but at least I was checking if I was awake. And that gives you Zn2+, which is what you've got there. And we know it's oxidation. Our electrons have to be on the right-hand side. And so here is a little, I would say last little bit of advice, because we're almost done, but we can do this. We're going to finish strong. If you see that it becomes 2+, that is usually the number of electrons that you'll write in your equation as well. A couple of minutes or hours earlier, we saw Ag, silver, Ag+, +1 electron. So you'll see that whatever number you have as your superscript, that is the same number of electrons. If your school, and you'll only know if you've done it, if you've looked at that SEP table, that table with all of the half reactions, then it's actually easier. You can just copy it, but that's grade 12. But there's a little tip for you guys if you don't know how to know how many electrons to add. Right. E, state the name for the above half reaction. So we know that that is now our oxidation half reaction. Right. So reduction was the hydrogen one. This is oxidation. Now define, and if I'm going to read it so that I don't confuse you, the action word define means what did you study, that exact definition. So the definition of a reducing agent, and even if you forget your definition, this is how you backtrack. A reducing agent, this is not the definition, this is an explanation. The reducing agent causes reduction, undergoes oxidation. Oxidation is loss. A reducing agent is the substance that loses electrons. So let's see, it's the substance that undergoes oxidation and therefore loses electrons. There we go. So even if you forget, I want to be very honest and say sometimes we do forget. Often we forget, trust. You're going to get in a test or get in an exam, and sometimes you really kind of feel like you hit a blank with the section or with the definition or with the formula. But sometimes also you can just figure it out a little bit. Okay, so reducing agent is the one that undergoes oxidation. That's my explanation. And therefore your definition is it's the substance that loses electrons. Right. G, identify the reducing agent of the above reaction. Give only the formula. So yet again, exam 101. If they say give the formula, it means the formula, your symbols and subscripts, and maybe brackets. If they say give the name, and usually it's in capitals or bold, the name would be written out. So hydrochloric acid or hydrogen chloride. Whereas if it's a symbol or if we say the formula, it is the shorthand version. And you do get to a point in your matric papers where we subtract marks if you don't write the correct format, I must say. Right, so identify the reducing agent of the above reaction. And we know now, and you can put them together and also just check. So let's do that. Right, let's do this. Hydrogen went from a plus to a neutral, and then zinc went from a neutral to a positive. So if this is the reduction reaction, then we know that this will be the oxidizing agent. I'm going to write it out. And if this is my oxidation reaction, then this must be, zinc must be my reducing agent. So your reducing agent is what your oxidation reaction starts off with. And your oxidizing agent here, your oxidizing agent is whatever your reduction reaction starts with. So they're asking us to identify the reducing agent. And so therefore we can say that that will be Zn. They asked for the formula. If they just say identify and they don't say formula or name, then you could have gone and written zinc. All right. In closing, we're going to look at this last little bit very swiftly. And then I'm going to open it up for questions. We've got 5 minutes left, so let's finish strong. Matthew decides to store a copper sulfate solution in an iron jug. Okay, so we have got Cu, SO4, and he is placing it in an iron jug. Okay, we don't really know whether they react yet. It's just they're in the same vicinity. Okay, so maybe let me, but these are the substances that you have. Give the formula of the ions in a copper 2 sulfate solution. So they're asking us in copper sulfate, we must give the ions. So now we do know from our polyatomic ion table, which I'm sure you should not be getting in exams, is SO4 2-. There is only one copper in this solution. Copper, if I say one copper, I mean in the formula, there's obviously millions of copper ions in the solution, but there is only one copper in this formula, which means that there is no subscript, right? So if the charge on sulfate is 2-, then it must be 2+. So it's going to be Cu 2+. And there you answered the question, because they merely asked us to give the formula of the ions in copper sulfate. And quite sneakily, they already said copper 2. So you should have known that it is 2+. All right, so Cu 2+ and SO4 2-. Cool, the last question, and I can sort of imagine that some of you are sighing and starting to stretch. Is Matthew wise? Explain your answer. Is he wise to place the copper sulfate in an iron jug? And this is where I want to come in with that SEP table, and I kept it for last. Some of us are not entirely sure how to answer this question. And so I would make a star next to this question. And remember the star, because if you haven't done it, this will maybe be above what we've done so far. And it's no one's fault. It's just how schools deal with their syllabus. But if you have looked at that table and you've looked at reducing agents and oxidizing agents, and I'm using my fingers because on the table, and I'm now so sad I actually didn't bring mine, but if you look at that SEP table, there's an arrow to the right hand side that points up and it says better reducing agents. Reducing agents undergo oxidation. So any substance that is higher up that table would take preference in undergoing oxidation. Okay, and on that same table, there's an arrow to the left that points down and it says better oxidizing agent, which means anything below an oxidizing agent undergoes reduction. So if you've got two substances on the list, it's a normal list with many half reactions. You just identify. So in this case, we're going to have copper and iron. Polyatomic ions don't appear on this table. It's usually your metals, right? Metals and some halogens. So you've got copper and we've got iron. So on that table, if you have one, or if you want to Google one later, then just check. It's called the Standard Electrode Potential Table, or SEP. And you can get one on Siavula as well. So if you look at that SEP table, you must identify where you've got iron and where you've got copper. And so in that, you'll see on the memo, they say, no, he isn't smart because Fe is a stronger reducing agent. So is he strong? Is he smart? No, because Fe, iron, is a stronger, and I'll explain now, is a stronger reducing agent. On the table, higher up is a better reducing agent, which means it will much rather undergo oxidation, and lower down is a better oxidizing agent. They will much rather undergo reduction. So by saying no, he isn't smart, Fe is a stronger reducing agent, we can assume, infer, deduce, whatever word you are comfortable with, that Fe is higher up the table. It's a better reducing agent than the copper, so copper should be lower. And why is he not smart to put the copper sulfate in an iron jug? The copper is undergoing oxidation. What does that mean? Your copper is eventually going to become Cu2 plus ions, and it's going to release or give or donate 2 electrons, which means it's going to be keen to form a different bond. So in the end, right? Sorry, not your copper, your Fe. Sure, it's been a long day. Your Fe, apologies, guys. That's what's going to happen to your Fe. So what does this mean? When you've got ions, they're keen to form bonds. So your actual jug is going to start reacting with the content. And therefore, he's not smart for keeping the copper sulfate in an iron jug. Okay, so that one I just wanted to work through, or actually just talk through, because I saw this and I thought, without an understanding of higher up, lower down, better reducing agent, whatever it might be, of that table, this question could potentially be very, very difficult. And you might sit with it for minutes and not know what you're doing. So make a star if you haven't done that SEP table, and then revisit this question once you have. This could also refer to the reactivity table, where we've got displacement reaction. So if your iron is a better, if it's higher up the reactivity table than your copper, then we know iron will kick copper out of the solution, and then it will form a solid precipitate. So I just wanted to mention this question because I did sit for a moment to think, if you haven't done that SEP table, it could potentially be quite challenging. All right, guys, we have reached the end. It is 6 o'clock. I am going to say thank you so much for working incredibly hard, and many of you participated and sent messages directly to me as we were doing calculations, and many questions were asked, and I do hope that everything was answered. If you've got any further questions, I am going to remain here for a couple of minutes. Please, please, please unmute yourself, ask the question, or type in the chat. But other than that, thank you so much for an awesome afternoon, and please look after yourself.